Let's begin. As usual, I recommend turning on your videos if you can. It's not necessary, but it's nicer in terms of, not lecturing to, uh, invisible audience. Okay, oh yeah, and before I begin, I hope some of you are attending some of the talks going on at the Simon's workshop on computational phase transitions that I pasted on Ditto. You should be able to still get a link, if you register. So fear not if you haven't seen any talks so far. Still many to go. Okay. So today, last time, I kept anticipating that, we're going to do unique games this time, but I actually realized that I need to do something before that, at least in the logical order of things that I had planned. And so, I'm going to do like this slight bait and switch on you and tell you instead about, approximating graph expansion. But it's a cool problem, and hopefully you'll have as much fun as I had in preparing this lecture. See how that goes. So for today, our goal would be to deal with graphs. As usual, they have vertex set V, at set E. We'll always think of the vertex set to be of size n. And today I'm going to look at only d-regular graphs. Now, strictly speaking, for everything that I'm going to do today, this d-regularity is not at all a necessary condition. You can basically make it work for arbitrary graphs. But some of the intuition about expansion, etc., is easy to glean if you deal with only regular graphs. So that's the reason I'm going to stick to regular graphs. But none of the algorithmic things we'll prove today will actually depend on regularity. Good. So here is one function that we've been playing with for quite a few lectures, which is this quantity 1/4 sum over all pairs of vertices that appear as edges of xi minus xj square. We kind of examined this quadratic polynomial to death in some sense. We observed that it's the quadratic form of what is called as the Laplacian matrix of the graph. It computes the size of the cut of the graph up to size of the cut of the graph when x is over plus minus 1 to the n. And we actually use this polynomial to phrase the max cut problem as a quadratic optimization problem over the hypercube. We found like an approximate solution for it, blah blah blah. Great. So in particular, we all know now that for any subset S of vertices, the set of edges that go across the cut, meaning set of all ij such that I is in S but j is in S complement. This is basically the cut, the edges in the cut described by the subset of vertices S. And we know that fg, if we compute at the plus minus 1 indicator function of the set S, then it simply computes E of S bar, the size. Good. And when we first started looking at f sub g, then we said, hey, min f sub g of x, where the minimum is taken over the hypercube, is basically the problem of computing the min cut or size of the min cut of the graph. And there is a one approximation algorithm for this problem. That's a funny way of saying that this problem actually has a polynomial time exact algorithm, as I'm sure all of you have seen. And as I said, we spent quite a lot of time examining the maximization version, which happens to be NP-hard, but we could still get like a decent approximation. If you remember, we proved 0.878 approximation. On the homework, in fact, you got like a finer guarantee, especially when the graph is like near bipartite. And so, we kind of understand, how the maximization business works too. So today, our goal is to do something very related to this min cut problem. And you can think of it as min normalized cut. Okay. And this quantity that I'm just going to define for you goes by like several different names in literature. I'll give you all of them so that you never get bothered by different words that people are using for the same quantity. um, but I am going to call it expansion, and I'll explain to you why I like that term just in a bit. Okay, expansion of the graph. So basically, what I'm concerned about is not the size of the cut, but some normalized measure of size of the cut, in the sense that I want to say that, hey, if the cut was described by a set of vertices s, and s was of, let's say, very small size, then it's not such a surprise that the cut had small number of edges. I mean, if one of the sides has only one vertex, what's the big surprise that the cut is small? So I kind of want to reweight the size of the cut, so that it takes into account the how reasonable the partition is. Like, in some sense, I want to measure the size of the cut proportional to some reasonable measure of how balanced the partition itself is. And I'm going to define normalized cut to get here. So what's this quantity going to be like? So I'm going to define, so this is the definition. I'm going to define normalized size of any cut described by a subset of vertices S as number of edges in the cut divided by, so I'm going to write an expression and I'll explain to you what this is, okay? So, in the denominator, I have d over n. Remember, d is the, degree of every vertex in our graph. So it's d over n times size of the vertex set S times n minus the size of the vertex set S, or basically, size of S complement. So what is this quantity in the denominator? We were saying, hey, you know what? Let's look at, a random graph where, the average degree of every vertex is, d. So basically, think of the random graph gn comma d over n. Okay. So each edge is present independently in this graph with probability d over n. Okay. In that case, if I look at any cut defined by a subset of vertices S on one side and S complement on the other side, well, what's the expected size of this cut? Well, the number of edges that go, the total number of possible edges that go across this is simply S times S complement, which is n minus S. And now each of these edges is present with d over n probability. So this is basically the expected number of edges in a random graph, across the cut defined by a set of vertices S. Okay. And so what we're saying is, hey, you know what? I'm going to compare the size of the cut. So this is my normalization, as I was saying, I'm going to compare the size of the cut in this d-regular graph at some subset of vertices S, to the size of the expected size of the cut, of the same set in a random graph with the same average degree. Okay. And so it seems somewhat of a reasonable measure, right? Like, hey, you know what? In expectation, a random graph's cut looks like it has this size. What fraction of this size do I actually have in my cut? Okay. Good. So, right. So that's phi g of S. And, now, just like min cut, I'm interested in, the minimum possible value of this. So I'm also going to make a definition for that. So minimum over all S subset V, so, in order to not be trivial, I need to force this to be a non-trivial subset of phi g of S. I'm going to define as phi g. And, this quantity I'm going to call the expansion of the graph. Okay. Good. So that's the normalized size, normalized size of the cut. And I guess one way to understand is basically it's measuring, what fraction of the size of the same cut in expectation in the random graph do I actually have in my graph. Um, One nice way to interpret this quantity is the following. Okay. And that also kind of explains, the notion of expansion. So suppose I start a random walk on G form a random vertex in S. Okay. And now, usually in the context of random graphs, one thing that we are usually concerned about is, hey, you know what? Is S a bottleneck set, in the sense that, how easy slash difficult is it for a random walk to escape a certain set S, given that, it starts, let's say, inside it. So here, we could ask, what's the chance that the random walk in one step goes out of the set S? So I began at a random vertex in the subset S, and I take like a uniformly random edge from that vertex, and I traverse to a new neighbor. What's the chance that I go outside? Okay, and if you compute this, this is exactly equal to phi g of S. Okay, and this is just a simple computation. And that's maybe one reason for why I like to call this expansion. It's like, in some sense, what's the chance that I go out at a random walk that begins at a random vertex in S, goes out. And in some sense, it's a measure of how connected the graph is, right? Like, if expansion is large, if every set expands, then it somehow says that there is no bottleneck for a random walk. The random walk somehow goes outside any given set fast enough, and in fact you can use it to prove that the random walk is fast mixing. Conversely, if there is some set which has like a small expansion, then in fact that set serves as a bottleneck for a random walk, and it provides a proof that random walk may not mix fast. Okay, especially if you start from a uniformly random vertex in that. Good. So hopefully you like this quantity, but by itself. But there are like several applications of this quantity, even if you didn't care about the two interpretations that I already gave right now. This quantity appears naturally in the context of graph, partitioning graphs. So I'm not going to go too much into details about this. The motto of this class is, whatever we decide for a day is like an interesting problem. So we don't justify too hard why that problem is interesting. But just to give a little bit justification, in any case, this is kind of a important primitive in partitioning graphs. So basically, the rough idea is the following, and this is non-mathematical, so I'm not going to write anything. But in many, graph problems, what you would like to do is, some kind of a divide and conquer algorithm. It's like you have a graph problem, you want to solve it. So one thing you could do is, well, if the graph was like really disconnected, like there were like two components in it, you could just like split the graph into two parts. And usually for many of the problems that you're interested in, you can just like separately operate on each of the two parts. Okay, now you kind of want to do the same thing even if the graph is like not like disconnected, but still somehow so the graph is completely connected, but you still want to do some kind of divide and conquer. So one thing you can do is, just find like the sparsest cut in the graph, like, the cut that has the normalized, like the least fraction of edges normalized in this way that we just discussed. And then usually what you can do is like split the graph across that set and operate on the two parts separately. And roughly in the analysis, you can use things like, well, the number of edges that were going across this cut were small in a normalized sense, so I can somehow, be fine with it. And so this is kind of an outline of many algorithms, which kind of which has this universal first step, like partition the graph into two parts and operate separately. And what we're going to see today, this algorithm for partitioning graph into two parts so that the cut is sparse, is basically an important primitive there. So anyway, like either you care about bottlenecks for random graphs, random walks, or you care about how large the cut is in a normalized sense, or you care about graph partitioning. Pick your motivation, because we're gonna like look at this problem in detail today. Good, very good. So let's look at algorithms for the problem, algorithms for this problem. So our goal is goal given a graph G. So it's always going to be n vertices and D regular. Our goal is to compute phi G, right? Like this minimum possible expansion of any set in the graph. So as has been the theme so far in the class, It comes as no surprise to any of you, I believe, that this is NP hard. And actually, this is not so hard to prove either. If I feel so inclined, I will, put it as like an exercise on your homework. But you can give like a reduction from max cut to this problem. It's like a paragraph long proof. So that's not so hard. But in fact, it turns out to be even hard to approximate in a certain sense. And in that direction, there's like this. There's like a famous paper of Chawla, Krautgamer, Rabbani, and Sivakumar that proves that this conjecture that we have anticipated a whole lot, talked about a whole lot, but never defined so far, implies, the unique games conjecture implies that, there is no constant factor approximation algorithm for this problem. So that's kind of surprising, right? Like for max cut, for min cut, we know is in polynomial time, so we can exactly solve it. Max cut, we can get a very good approximation with SDP rounding, but if you just wanted a constant factor approximation algorithm for max cut, you could simply return a random cut. It already gives you a half factor approximation. But we are saying, hey, you know what? Here is a variant of these two problems, which just measures the size of the cut in a normalized sense, and you want to minimize it. And actually, it's likely that there is no constant factor approximation algorithm for this problem unless, the unique games conjecture is false. Good. So actually, given that I'm saying this, let's maybe examine this simple quantity. What does happen to a random cut? So, what is this? So, if I were to just, take my chances and return a random cut, so just return a, uniformly random subset S of vertices, what's the size of the cut do I see? Like, what's the normalized size I get? So you can actually, quite easily analyze this, So let me just claim and not, do this calculation, but, you can very easily analyze that, the expected Pg of S for a random set S is like, theta 1. In fact, it might actually be at least half or something. And, the quantity we are looking at is at most 1. So, what this is saying is that, we can, a random cut only guarantees that, the normalized size is at least half, but the minimum could be very, very small, right? Like the graph could be disconnected. So the minimum could literally be 0. And yet, we are returning a cut of normalized size half. Remember, our goal is minimization, not maximization. It's no surprise that, we can maximize up to a constant factor, but, this goal of minimizing this normalized cut size, a random cut is no good. And so, great. That's not, I mean, it's not a big surprise, but, basically there is not just like this, it's not just about this random cut algorithm, but basically we don't know any algorithm, and we expect that there is no such algorithm that can get a constant factor approximation algorithm in polynomial time for this problem. Good. So, we're going to see something worse than a polynomial time algorithm today. It will still be quite good, but, it won't be constant. It won't give a constant factor approximation. So good, but so this problem is NP hard, also hard to approximate. So we are in our familiar land. We can ask, okay, what can pseudo distributions do? How good are SOS certificates for this problem? And the first thing you can ask is, what can degree 2 pseudo distributions do? How good are those? After all, we derived quite a bit of mileage, out of just degree 2 pseudo distributions so far. And so it turns out that they are not completely bogus. They do something quite non-trivial and quite nice here. And so, here is like a rephrasing of what is a pretty famous result called Cheeger's inequality. Many of you might have seen this in other contexts. If you've seen like any analysis of, convergence of random walks, etc., you might have seen this inequality. If you've seen, I don't know, if you took any class on random graphs and expansion, etc., you might have seen this inequality. I'm just going to write it in a slightly awkward way because I want to stick to our notation and language. So the attribution for this, actually, Cheeger never proved it for finite graphs. Cheeger proved a version of this inequality which holds for Riemannian manifolds, which I don't understand very well. But basically, um, a bunch of people found like a generalization of it to finite graphs. So I think the right references are Dudziuk from 84 and independently Alone and Millman from 85, and then a follow-up work of Alone in 86. All these people, basically formalized an inequality that I'm going to write down now. So they, proved in our context that for all D regular graphs G, same context, V equals N, FGX, oh, okay. Before I write down this inequality, I should make one comment. So let's maybe make it in yellow. We just described this quantity. We just described this phi g quantity as minimum over all x in minimum over all s in V, s non-trivial, ESS bar over D over N, S, N minus S. Good. So I guess, I want to first translate it into a form that looks like, some polynomials appearing somewhere. That's not so hard, I'm going to write this as plus minus 1 to the n. So now, we already know that the cut size is computed by this fg of x function. Now, the denominator I also want to write as a degree 2 polynomial. And I in fact claim that it's the same as this polynomial. Okay. And this is quite easy to verify. So let's just do it so that I don't lose you at like some trivial point in the lecture today. So, the point is, what is this sum xi minus xj squared? Well, the point is, x is like, let's say, s is the indicator of all the coordinates where xi takes the value 1. Then, xi minus xj square takes a value, there should be a 1/4 here. So xi minus xj square times 1/4 takes the value 1, if and only if, I is in S and J is not in S, or vice versa. And, if they're on the same side, then in fact, this expression takes the value 0. And so, therefore, this is just going to count the number of edges, all potential edges that can go out of S. So it's basically S times N minus S. That's what this expression computes. And, that's what we wanted over here. And so I just scale it by D over N. Okay, so hopefully it's not that much of a mystery why this expression is right. So that's great. But there is like one, potentially problematic issue here. It's like, the way we've stated this phi g quantity is a minimization over the hypercube of a quadratic polynomial in the numerator divided by a different quadratic polynomial, in the denominator. So it's not a polynomial, it's a ratio of polynomials of degree 2. And, that looks a bit awkward. We've never actually studied how to, minimize / maximize rational functions. But fear not, because this is just, demanding us to just rearrange things. So here's the point, okay? Suppose, I have a rational function of this form. So Px and Qx are polynomials. And let's say, I'm interested in minimizing it. Let's say the minimum value happens to be alpha, okay? Then that's the same as saying that Px minus alpha times Qx is non-negative. You agree? Like if the minimum value of Px over Qx over, let's say, the hypercube is alpha, then Px over Qx for every x in the hypercube is at least alpha, and just like rearrange, you get that Px minus alpha times Qx must be, non-negative. So, if I wanted to somehow minimize this ratio or prove, certificates for its minimum value, then that's the same as, finding certificates um, for this degree 2 polynomial, px minus alpha times qx. Okay. And so, let's just, label this box as an aside. It's like, even though we are dealing with rational functions, it's not that big a deal. We can still work with our tool. Good. Very good. So, okay, so now I can state the alone Millman, etc. inequality for you. So for all d regular g, fgx minus c times d over n sum ij xi minus xj square has a degree 2 SOS certificate. Okay, let's call it a theorem. For so actually, if I don't set anything, this is of course a trivial statement, because you can simply set c equals 0, and fgx is already a sum of squares, so no big surprise there. So real question is, for what c is it, does it have a SOS certificate? And notice that we would like c to be as large as possible, right? Like we are trying to minimize something. So when you think of from the certificate angle, you would like to have this certificate be true for as large a c as possible. Okay. Like notice that if I only wanted this to hold for some c, then it clearly holds for c equals 0. Okay. And in reality, you know that this polynomial is positive as long as I choose c equals phi of g, right? Because we know that fgx is at least phi g times this quantity on the right here. In real life, this is a non-negative polynomial so long as c is at most phi of g. Okay. But we don't because we already stated that this problem is NP hard, etc. We don't expect like c equals phi g to work for degree 2 SOS certificates. Instead, what we will show is, actually I'm not going to show this theorem, uh, but what alone Millman, etc. proved is that there is a SOS certificate of this form for c equals half of phi square of g. Notice that phi square is usually going to be smaller than phi g. And so, this is saying that, well, in real life, I know that this polynomial is non-negative over all of the hypercube as long as I choose c, at most phi of g. But I can't quite find a degree 2 SOS certificate for it. But if you like, make it slightly smaller, and this time it's not like a constant factor approximation. It's like this weird approximation, where phi g goes to phi square of g up to some half factor. Then, in fact, it does have a SOS certificate. Okay. Now, so this theorem has a relatively simple proof, and in fact you will prove it on your upcoming homework. This is going to be a guided homework exercise for you. It's going to be simple, not that hard to prove. So let's examine how good it is, because we are soon going to somehow improve this theorem, which is going to be our main focus today. So So actually, before doing that, let me maybe state an algorithmic version of it. So, we've always been stating things as existence of degree 2 certificates for polynomials. But, as you've seen in the past couple lectures, the way we prove it is by analyzing pseudo distributions and really giving like an efficient rounding procedure. So that's also going to be true for this theorem, as you will show in the homework. So further, given any pseudo distribution mu of degree at least 2, such that fgx minus c tilde e mu d over n is non-negative, we can find a set S with expansion Pg of S equals O of root C. So what this is saying is that, if you give me an SOS, like, so the way we'll prove it is by, working with the dual statement. We'll prove that, if you give me any pseudo distribution that tells me that, the ratio of the edges going, across the cut defined by X, when compared to the number of edges that go across the same cut in the random graph in expectation is at least C, then I can find an actual cut which has at most O of square root C normalized a number of edges going across it. Remember, root C is going to be larger than C because C is less than one quantity. So, the pseudo distribution in some sense is pretending that, there is a cut of normalized size, at most C in the graph. And while, we are saying that, okay, if the pseudo distribution does that, then we can find a cut whose normalized size is, not too much larger. So O of root C. So the reason I'm, saying it out in English so often is because so far we've been dealing with maximization problems. Today we are dealing with minimization problems. The switch can be somewhat confusing. So, hopefully my redundancy in repeating things is helping you out, just giving you a pause and letting you think it through. Actually, let me help you doing that by taking a 30-second pause and taking any questions.
Okay, so I have a silly question, just pattern matching stuff here. You have, you can get something with root C, and then the pseudo distribution has basically like phi squared of G. So why does that not just give you like up to constants, the like correct thing?
It's a good question. So let's think about it. Like, what would you do? So, okay. So this is a good question, and it kind of will clarify notation, etc. So let's do it. Let's answer, this question somewhat in detail. So what are you going to do? Like, if you wanted to like look at it as an algorithm for computing a set with low expansion and not just, finding a certificate, what would you do? You'll say, okay, you know what? Find, so this is also an aside. So find a pseudo distribution mu such that, C is, let's say, bigger than or equal to 0. So this is a constraint you can put. And you can also, say that I want to do this for maximum possible C. Right? So you can try to find the maximum possible C for which, this inequality holds, for the pseudo distribution mu. Right? Now, the point is this. If this pseudo distributions for actual distributions, then in fact, that, the value of this program has to be phi of G. Because, the expansion of, like, there is a set, that has a normalized cutoff size, exactly phi of G. So you can't quite use, something bigger than that. Okay? Agree? But given that, you're asking this program to search over pseudo distributions, in general, because pseudo distributions are not the same as distributions, they are like a slightly larger class, you'll potentially be able to find something that does better. Right? So it might be able to find, so in general, it's going to pretend that there is a normalized cut of size much smaller than phi of G. What we're saying is that, well, if it does that, so, whatever cut size it pretends that there is one in the graph, I can find something which is like not too much larger than it. So, even though pseudo distributions can be fooled, that they can in some sense do better than what, true cuts size are, they can't be too far from it up to the square root factor. So in fact, this square, like the fact that C went to square root C is the same as phi G went to, phi square of G up to constants. Does that answer the question? So think of it as a minimization problem. The relaxations value, it's a relaxation after all, because we are searching over something more general than distributions. It's going to be usually smaller. What we're saying is that whatever value it returns, we can, return a cut of, a cost which is not too much larger. In fact, it's going to be larger only by like the square root factor. Okay, does that answer your question?
Yeah, I think so. Thanks.
Okay, good. So good. So as I said, you're going to prove this on your homework. Oh, and I guess I should mention this before moving on. So when sorry about that. Google tries to help me in research, but it's not very good at teaching. So right. So when Fiji is large, this is actually not so bad an algorithm, right? Um, if Fiji is a constant, then this tells me that there's a certificate which basically which is like a tinier constant. There is a degree 2 SOS certificate, and so it actually is a constant factor approximation algorithm if phi of g itself is a constant. Okay, so in other words, if I have a graph where every cut has normalized size at least a constant, then in fact I can certify that every cut has size at most some tinier constant. Right? I can certify that in just degree 2 SOS proofs. So that's kind of good. And in fact, such graphs are extremely important, and I'm sure you've seen this before. They're called as expander graphs, where phi of g is a constant. And so in particular, this alone Millman inequality allows you to certify that certain graphs. So if a graph is an actual expander, it allows you to give a degree 2 SOS certificate that it is indeed an expander, and it loses only a constant in this process. When is it weak, on the other hand? Well, when Fiji is small, so when the graph is not an expander, when Fiji, is some quantity that goes to zero, as n tends to infinity, well, in that case, the approximation is weaker. It's in fact, a factor phi of g approximation. So, if phi of g is like, 1 over log n, then it's a log n factor approximation, etc. And so, that's when it is weak. And in fact, you can have graphs where Fiji is like 1 over root n, and then it's like a really, really bad approximation. And so what we're going to do now is, basically improve this particular degree 2 proof in the regime when Fiji is little o of 1. Because, when Fiji is large, in some sense, it's all good anyway. When Fiji is bigger than a constant, this alone Millman stuff already does the job, and you will prove it on your homework in a relatively simple proof that in fact it works quite nicely. So today what we're going to do is like improve on this result when Fiji is little o of 1. Okay, good. So a little bit of historical note on this. So, I told you this was happening around 85, 86, this alone Millman inequality. Oh, I promised you different names for this problem, but I forgot to tell you that, right? So, okay, we've used expansion so far. But, some people also call it the uniform sparsest cut problem. And this is not so surprising. Sparsest cut or uniform sparsest cut is basically some way of measuring how dense a cut is, and you're trying to find something which is very light, in this normalized sense. So it's not such a bad name for it, and people use it. Anyway, so in '88, which is like maybe a few years after this alone Millman inequality was discovered, Layton and Rao discovered a linear programming algorithm that gives a order log n approximation. So let me in fact state it as a search algorithm. So whenever, so okay, actually, see, given a graph G, D regular, blah, 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 can find in polynomial time a set S such that phi G of S is O of log n times phi of G. So, the expansion of the set I find, so I'm trying to find the least expanding set. The expansion of the set I find is going to be at most like log n factor worse than, the true smallest possible expansion. So, in particular, this is better than the alone Millman inequality if phi of g itself is like, smaller than like 1 over log n. So, let me just say that improves phi of g is, much, much smaller than 1 over log n. So that's kind of nice. That's good. And actually, I'll give you a proof of this of this theorem. I mean, I will not use any programming. I'll give you a proof of this theorem along the way of the stronger result that we'll show today. So that's good. So that was the linear programming thingy. And then actually, for a long, long time, it was a huge open question whether this can be improved. And it was finally improved in kind of a breakthrough work due to Arora, Rao, and Vatsirani. So this is Sanjeev Arora, Satish Rao, and Umesh Vazirani. And they proved that, on the same setting can find a set S such that phi g of S is at most O of square root log n times phi g. So it's a square root log n factor improvement over this linear programming based algorithm. In particular, this now beats Cheeger inequality when phi sub g is smaller than 1 over root log n instead of 1 over log n. So that's quite nice. And their algorithm is based on degree 4 sum of squares. So that's what we're going to do today. But before I do that, I want to make like some high-level non-mathematical comments or like pseudo-mathematical comments. So, well, first, that ARV were not talking in this language of SOS, but this you already know. Gomans and Williamson were also not talking about degree 2 SOS when they wrote their paper, and that's also what ARV were not doing. So they were talking in this prehistoric or classical language of talking about SDPs in terms of vectors, which in this class we have given up. But we will describe it in our language. Okay, we will describe this algorithm completely in our language, and hopefully it would be enlightening in that form. So the other thing I'm going to mention is that this is our first instance where going beyond degree 2 is truly going to help. Okay, so on the homework, you will not only analyze and prove the Alon-Millman inequality, you will also prove that it is tied up to constants. So this phi to phi square or c to square root c relationship that I claimed in the theorem, in fact, cannot be bettered. And the example of a graph where it actually fails would be very, very simple. It's the same example that you've currently been analyzing, for MaxCut. It's the cycle. And so, you will prove on your homework that, just for the humble cycle, this degree 2 certificate for expansion of Alon and Millman is tight. So you cannot improve it. So, certainly you need to go beyond degree 2 if you wanted to improve it. And, this is the first instance, first striking instance where going beyond degree 2 does give you an improvement in a certain form. Okay, so that may be the first point. The first instance where degree 4 SOS helps. That's great. The other thing I want to mention is that so far we analyzed a number of algorithms, for MaxCut and for quadratic optimization and stuff like that. And in each of these cases, at least, barring one case of this nested-O theorem, our analysis was local. So far, we've been doing local analysis of the rounding. What does that mean? Well, usually what we do is like we do this Gaussian rounding, meaning we draw a Gaussian which has the same first and second moments as the pseudo distribution given to us. And then we kind of analyze what happens in expectation to a single, constraint in our, in our system. So for example, remember for MaxCut, what did we do? We said, hey, you know what? Let's analyze what happens to a single edge. So we said, okay, if in the context of MaxCut, we related, quantities like xi minus xj square and, the rounded distributions value, right? So I'm going to call such analysis, which kind of, relate things on constraint by constraint basis. And constraints usually depend on constant number of variables. So, this is basically analyzing the rounding at a constant variable level in expectation. I'm going to call this a local analysis. And so far, barring the nested-O theorem, where there was a certain piece of global analysis going on, our analysis of the rounding was, local. Today, we will see this example of ARV is also our first example where a global analysis truly helps. Okay. In fact, what I'll do today is first give you like a very simple local analysis roughly along the same lines as ARV that recovers the latent row theorem that gives you order log n approximation. So local analysis immediately gives you order log n approximation algorithm, and then will improve it by a global analysis. So roughly the idea of global analysis is that hey, you know what? So let's do like a pipe dreamish version. How global analysis could have helped in the context of max cut. It doesn't, but how it could have helped. Well, let's say that you drew like this Gaussian from the same first and second moments, and then you calculated the probability that for a single edge the rounded values somehow are on different sides. Like even though let's say e mu xi minus xj square was, let's say, some large quantity, so this edge was like somehow supposed to be cut. When we rounded, xi prime and xj prime happen to be equal. This is the point where we lose an approximation ratio to max cut, right? Like in expectation, we showed that this won't happen, whatever, like 0.878 factor times this e mu xi minus xj square times. But in terms of actual cut that we get, we're going to get a small value when xi prime equals xj prime. So in a pipe dreamish world, you could do the following. You say, what? If somehow it happens that xi and xj were like separated in the pseudo distribution, but they got the equal value in the rounded distribution, somehow this should not happen for too many edges at once. Like maybe there is some way to collect all these edges together for which we are failing, and then argue that, hey, what, you actually this can't happen, even though in expectation for each given edge I was supposed to fail for a fixed constant probability. I cannot somehow fail on a large number of them at the same time. So there is some hope that you could do some global analysis which could give you a potentially better approximation ratio than the one that we got in expectation. Of course, this is not true for max cut because well, you already analyzed the cycle on the homework, I believe, and we already know integrality gap which improves on the cycle. So this is not going to work for max cut, but today we'll show that this kind of global analysis will help for sparsest cut or uniform sparsest cut or expansion. Okay, good. So that was the non-mathematical pontificating part. I'm done with that. So we'll do some math now. Oh, guess I'm not done. I want to tell you one more thing. That the way we prove this, so my reason for choosing this, so you already see two reasons for why I'm choosing to do this particular algorithm. One is that it's the first usage of degree 4. Second is that it gives you a way to the first foray into global analysis of the Gaussian rounding. But there's like a third very good reason, which is that actually the same proof style eventually, it was not at the same time, but once ARV came out in like the next 5 years, people discovered a similar global analysis that improved approximation ratios for several problems. And one of them is vertex cover. The other is like coloring coloring 3 colorable graphs. So this is like the coloring problem. There's also this version of max cut where we're trying to where we are trying to minimize the number of uncut edges, and we want to measure our approximation in terms of how we are doing on the fraction of uncut edges. All of those you can improve. And if I am so inclined, which I feel like I am going to make one of these a homework on your upcoming homework number 3. So yeah, you'll see how you can use ARV to do more stuff than just expansion as today. Okay, good. So now I am truly done and I can tell you the math. Very good. So here is the theorem that we will prove today. So G deregular, same setting. Then there's a degree 4 SOS certificate for the following polynomial: FGX minus D over N IJ. So this is so far the same. The only question is, what do I place here? What constant should I place here? And I'm going to say that this is going to be some constant times square root of log n. Okay, and that's going to be our main theorem. In the certificate form, that's what it is. Perhaps this is more easily appreciable in the algorithm form. So let me maybe say that given any degree 4 pseudo distribution mu on plus minus 1 to the n. Okay, I feel like I might be forgetting this factor 1/4. Hopefully you're not going to be too bothered by it. At the end of the lecture, I'll go back and put 1/4 wherever I missed. But hopefully you're still following. Good. I mean, there are lots of constant factor losses, so this 1/4 should not bother you really. But all right, so can find a set S such that phi g of S is at most O of square root log n times whatever the pseudo distribution is pretending to be pretending that the expansion is. All right, can find in polynomial time. So that's the rounding version of the same theorem. Good. So in particular, this is a order log n, order square root log n approximation, to the expansion of the graph. Good. So let's start this proof. So it's slightly it does involve like slightly more technical work than I guess what we've been doing for MaxCut. So I'm just like bracing yourself, but it's not so hard, and we'll be able to do essentially the proof fully in the remaining time. But we'll go slowly. And first, as I told you, we'll see some weaker results along the way as we prove this theorem. Okay. So let's think about this, right? Let's try to prove this rounding side, right? Because that's how we've been proving the existence of certificates so far. So we want to prove this theorem, right? We want to prove that given a pseudo distribution where, this ratio kind of pretends like some number, how can we find a cut whose expansion is no larger than like some square root log n factor than times, this pseudo expansion value that the pseudo distribution returns, okay? So, and actually, you should also be wondering, how is degree 4 going to come in here? Like, how are we going to utilize the fact that, we have a degree 4 pseudo distribution, not just a degree 2 one? So here's one way to think about it. Let's look at, this quantity. So for every pair ij, I have this quantity. Let's understand what this quantity means, okay? So we already know that, so if there was no tilde on top of my expectation, and in other words, like if mu was an actual distribution, then, this quantity is 1 if xi and xj are unequal and 0 otherwise. So this is simply the pseudo probability that vertices I and j are separated. So, like this pseudo distribution is giving you a pseudo, this pseudo distribution is a pseudo distribution over, cuts in the graph. And you can ask, okay, if I take like okay, the following sentence makes no sense, but still hopefully makes some sense. If I picked an S according to the pseudo distribution and, calculated the probability that I and J are on the same side in that cut, well, how often does it happen, What's the probability that, if I picked an S at random from this distribution, what's the chance that I and J are cut? Of course, it's a pseudo distribution, so this is kind of a meaningless statement, but that's how we are supposed to think about this quantity. So in particular, this quantity, is at least 0. Can someone tell me why this is at least 0 while I write the next thing? So why is this quantity at least 0? It's a trick question, but feel free to unmute yourself.
Mitali says it's a square.
Yes. So remember what degree 2 pseudo distributions are. In fact, there's a degree 4 one, but which only makes it easier. So all sum of squares polynomials of degree 2 must in fact get a non-negative value. In fact, this is a degree 4 pseudo distribution. So, sum of squares of even degree 2 polynomial will get non-negative values. So of course, this is going to be non-negative. So that's not a big surprise. But, we just, we didn't quite argue, but you can actually quite prove very easily that this is also at most 1. Okay. And so that's great. So let's call this quantity capital Dij. You'll see in a second why I'm doing that. Okay. Capital D is soon going to stand for distance. Okay. But we'll see why I can think of this quantity as a distance in a second. So now comes the point where I'm going to make use of the fact that I have a degree 4 pseudo distribution, not just a degree 2 one. And I'm going to use something that hopefully you've already proven on homework 2. So on homework 2, you proved or are going to prove the squared triangle inequality. I mean, ignore the 1/4 really, but just want to carry them around because that's what I care about. So this was the square triangle inequality, which hopefully you established already on your homework. In particular, this holds for degree 4 pseudo distributions, and you used / are going to use it to show that a cycle in fact is not a bad example for degree 4 pseudo distributions for the max cut problem. So hopefully you did that or are going to do that. But in fact, that's the only consequence of degree 4 pseudo distribution that we're going to use today. The fact that degree 4 pseudo distributions can prove this squared triangle inequality. Okay. Good. So that's great. That's great. So in particular, I can, in my new notation of capital D that I just defined, I can write this inequality as saying Dik is at most Dij plus Djk for all triplets Ijk. Okay. So now hopefully you buy, this notation of calling this tilde e mu of xi minus xj squared as capital Dij. Okay, so because it's a bona fide distance, it satisfies a triangle inequality. So I can call it a distance. And so I'm going to do just that. Okay. Now, one thing I want to mention is the following. Discover homework problems while actually teaching. That's very great. So the following is easy to prove, and I might put it on your homework, that for any degree 2 pseudo distribution, this is true. This is like the non-square triangle inequality. Okay, and this is actually very easy to prove. Actually, let me just speak out the proof and then still include it on the homework. So the point is that you can just like take a Gaussian with the same first and second moments as a mu, and then this inequality, and because this is only computing degree 2 expressions, this is inequality about true expectations of Gaussians. And then this is just simply the L2 triangle inequality, the usual triangle inequality in Hilbert spaces. Okay, so this is actually easy and holds for all degree 2 pseudo distributions. But notice that the inequality I have up here is stronger than this square rooted version. Okay, this is what I want you to notice. If I squared both sides of this square rooted inequality, which actually happens to hold for degree 2 pseudo distributions, then on the right hand side, I actually get like this, cross term. Okay. So if I were to somehow just work with degree 2 pseudo distributions, I would not get this inequality. In fact, this inequality is, really requires the fact that we are working over pseudo distributions over the hypercube, etc. Okay. So I just wanted to point out that, there is something very non-trivial going on with this square triangle inequality. In general, it is not supposed to be true. Okay, good, very good. Okay, very good. So, okay, so as you said, as you saw, we have a metric on the n vertices coming from the SDP solution, coming from degree 4 sum of squares. That's very good. So our goal is, to find a cut that is, small in a normalized sense, right? But before doing that, I want to solve the min cut problem. Okay, I want to solve the problem where I didn't care about the normalized size. I cared only about the size. Okay, I want to show you, because it's like a motivating case for how to round, and because it is so simple, I want to do it. It's kind of fun. So let's say, I just want to now, as a first step, I just want to find a small cut given a degree 4 pseudo distribution. Okay, given a degree 4 pseudo distribution, and the cut, it pretends that, there is a value of the cut, that there is a cut, which cuts at most till the e mu of fgx edges. I want to find, a cut that cuts no more number of edges than, what this pseudo distribution pretends. Okay, so I want to solve the min cut problem with approximation factor 1. Okay, so let's do it. So I was, when I was trying to do this a couple hours ago, I thought the right analogy for it is, using sledgehammer to crack a nut. That's the right saying in English, right? It's like, we're using degree 4 sum of squares to solve a problem that all of you have seen like several times and know very simple algorithms for. But sometimes it's nice and fun to, crack nuts with sledgehammers. So we'll do that. Okay, so here's the key idea. We want to use the fact that capital D is a metric on the vertices. Okay, so here's what we will do. Take any vertex. So, let's label the vertices as, in any order as 1 to n. Good. And now, map every vertex to the point D1j. So, map vertex number j to this distance of it. So, map vertex j to the number which is basically equal to the distance of it from the vertex number 1. So what have I done? I've just like laid down the vertices on a line. Said, okay, I'm going to somehow, put vertices on this line in the order of their distance from vertex number 1. Okay, so I have vertex number 1 here, which is at a distance 0 from 1. Then let's say, that this order that I chose happens to be the right one. So the second vertex is at D12, third at D13, and so on up to, D1n. Okay, good. So as we already argued, Dij's are non-negative, D1j's in particular are non-negative, and D1n is at most 1 because, these were pseudo probabilities. So, I basically have a map from the vertices onto this interval 0 and, something which is at most 1. Okay. So now here's what I'm going to do. I'm going to give you a distribution over cuts. You're already familiar with randomized roundings now. So what I'm going to do is choose a number t in the interval 0, 1 uniformly. So just choose a random t in 0, 1. Okay. And output the following set. So set of all vertices at a distance at most t from the first vertex. So what I did was, so pretend that, this maximum thing was actually exactly 1. Okay. And saying, okay, pick a number, uniformly on this line. Okay. And then, just like randomly threshold it. Take all the vertices that live on this side. on one side of the cut and take all the vertices that fall here on the other side. Okay, that's great. That's what I'm going to do. Let's analyze the expected size of this cut. Okay, and as you'll see, I'm going to do a very local analysis just using the triangle inequality that capital D satisfies. Okay, so let's understand what's the probability, what's the chance that any edge, let's say I comma j, is cut. What's the chance that I comma j is cut? What's the chance that I and j, end up on opposite sides in this algorithm? Well, let's say that, j is bigger than I in this ordering. So let's use yellow again. So let's say j appears here, I appears here. Okay. Now, the only way I will separate I and j is if this threshold t falls, in between I and j in this line map, right? If t appears here, then I and j both will be on the right hand side. If t appears here, then I and j will both be on the left hand side. So the only way I separate them is if I happen to choose the threshold t, which is exactly between I and j, right? Very good. So what's the chance of that happening? Well, this is exactly equal to d1j minus d1i. Yeah, well, that's it, right? Yeah, that's it, right? And we assume that, j was further. Otherwise, you can just put an absolute value over here. So that's kind of good. And now here's the only thing I'm going to use. I'm going to use that by triangle inequality, d1j minus d1i is at most dij. And actually, the same thing also holds for the negation of the left-hand side. So it, and in fact, holds for the absolute value. And that actually, I want to say is, at that point, I can basically just like, draw the square. I want to say I'm done. I've found a cut of the, I have found a distribution over cuts whose size and expectation is at most the size of the pseudo distribution's value. Why is that? Well, we just proved that, this guy is at most dij, which means that expectation fg of s, this is the rounded distribution. This just splits into, sum over all edges. Now I apply linearity of expectation for each edge. For each edge, I just proved that the probability that they're cut in the rounded distribution is at most the pseudo probability that they're cut in the pseudo distribution. So we've literally just established this inequality. Linearity of expectation, blah, blah, blah. And so we actually found a cut, which is, at most the size of, the pseudo distribution's cut value. So we've solved the min cut problem. Like if you just like minimize the right-hand side over all mu's, then, you would get over degree 4 pseudo distributions. Then you found, you can round it to a min cut. So hope you're impressed. I gave you like a very new min cut algorithm now. Good. Any questions so far? Let's take a 30 seconds pause. Feel free to unmute yourself and ask questions. Okay, very good. So everything is crystal clear. That's great. Now, in fact, I want to observe something better about this procedure. So, you just saw like one procedure that outputs in expectation a cut whose size is no more than that of the cut, that the pseudo distribution is pretending like exists, right? This is basically, a verbose way to say the simple mathematical statement that, EFGS in this procedure that we just invented is at most e to the mu of fg of x. We can always, get a cut of at most the same size as the pseudo distribution is pretending to be. That's great. In fact, I want to observe a slight generalization of this procedure, okay? Because you're going to need it. So let A be any subset of vertices. Okay. So let's maybe write it as generalizing this procedure. So let A be any subset of V, and let's define DIA. So now A is a subset of vertices. What I'm going to do is define the distance of I from the set of vertices A as simply the minimum possible value of the distance to any J. So, like find the closest point to I in A. And, the distance to it is basically the distance of I to the set A. Okay. So this is not so surprising. This is a definition. So let's maybe remind ourselves there is a definition. And now, here is what I claim we can do. The same analysis works if you start from the line embedding DJA. So what does that mean? In the procedure we just discussed, we started by putting all the vertices on a single line, and we arranged them in order which was like in the order of the distance from the vertex number one. I'm saying instead of doing that, if you now do it with respect to the distance from the set A, the same thing actually works. So any vertex in A would end up at 0. Okay. And a generic vertex J would end up at point D JA. And it's still true that the maximum is at most 1. Okay. And now, so I'm not going to do it in too much detail, but the same proof, if you were to somehow check out what's the chance that a edge is cut, what's the chance that edge IJ is cut? Well, so it's going to be DIA minus DJA. And again, by triangle inequality, you can convince yourself that this is at most DIJ. So the same thing works. Now, in order to motivate, how this is going to relate to our, our approximation and our analysis for expansion, I want to ask one question, which is, in making both these claims, I have cheated a little bit. And I want to ask some of you why, haven't I actually given you an algorithm for min cut yet? So I gave you like 2 roundings, and it seems like ostensibly I argued that, it's going to give you a cut that has size at most the pseudo expectations value. But now I'm saying that I lied a little bit. What did I lie about? Wait, are there answers in the chat? I'm sorry, I'm not looking at that. Yeah, Jason is absolutely right. I never argued that I'm outputting a non-trivial cut. It's very easy to match the pseudo distributions value if I simply, return S equals the set of all vertices. In order to make this meaningful, I have to argue that, the cut is non-trivial. Okay. Do all of you see it? Like, for all I know, in here, for example, when I was placing them all the vertices on the line, well, what if, so all we know is that, there is a vertex. So the farthest vertex we know is at a distance of at most 1, but what if it's a distance 0? Well, then I'm not going to cut any edge. That's fine. But I'm also not going to give you a non-trivial cut. So it's completely bogus. I did not give you a cut at all. Right? So, it's not so much of a problem in terms of the min cut algorithm. I really, should choose a number t here, not in 0, 1, but, in 0 din or d1n, etc. But you'll see that it's actually a bigger problem in the context of rounding for expansion. So now let's understand why we are not done with the rounding for expansion. Okay, so certainly I can do this procedure, right? Certainly I can find a distribution over cuts whose size of the cut in expectation is smaller than the pseudo distribution size. So what happens to, so let's analyze this procedure. For expansion now. So and it's basically the same problem, except now in a quantitative sense. So in the context of min cut, all we wanted was that the cut be non-trivial. In the context of expansion, we not just want that the cut be non-trivial, we want the cut to be balanced, as you will see in a second. So now remember what our goal is. Our goal in the context of expansion, is to find a distribution so that after rounding, FGS.
Ish. I think the screen, like the screen you're sharing, seems to be frozen.
Oh no. Okay, let me share again. Thank you for pointing out. Is the screen moving again?
Can you write something? Yeah, it's working.
Okay, great. Thanks, Peter. What was it going on for long? Like, do I need to go back?
I think it was just going on for like a minute-ish.
Okay. Okay, very good.
Took me like a minute to be convinced it wasn't just me.
Okay. All right, great. So, yeah, I guess I didn't really write down anything in the last minute except that, I guess the only point I was trying to make is that, this issue that the cut may not be non-trivial is going to affect us much more strongly in the context of expansion. And so why is that? So remember, our goal is to, so let's call it X prime because it kind of helps us. So our goal is to find an actual, like all roundings, our goal is to find a distribution on X prime in, let's say, plus minus 1 to the n, so that the ratio of fg x prime, so the cut size of x prime in the graph G, over d over n expectation x prime I minus x prime j squared I comma j. Wait, what? So we are interested in this quantity, which is basically, the expansion quantity. We are, we are interested in, proving this is small. So we want to find a distribution over x prime so that this quantity turns out to be small. And we want to compare it, of course, to the quantity where the, these e's are replaced by pseudo expectations with respect to mu. Now, we already, convinced ourselves that, matching this numerator is not that hard. In fact, we can always stay below the numerator. So we can always, find a distribution where EFGX prime is at most e twiddle mu of FGX. But the question is, for, maintaining this ratio or, proving that the ratio is not too large, we have to do the opposite direction of the inequality for the denominator. So now we need that E of, so, okay, let's write D over N outside. Is at least the same expression with, the twiddle mu appearing. So, okay, good. And the point is that this is an opposite direction of the inequality. So the kind of analysis we did for edge by edge is in fact going to give us the reverse direction. But we want to lower bound, the size of the set we output and not upper bound it. And so that's our, that's the pickle we are in right now. Like we have to somehow, simultaneously make the numerator small, but, make the denominator large. And the denominator large is same. So, we already convinced ourselves that this is same, for any given x prime, this is same as, if you look at the set indicated by x prime, then we said this is the size of the set times size of the complement. So that's what this quantity is inside, which is basically, up to some constant factors, related to the size of the set that X prime denotes. So basically, this quantity is trying to tell us that, we must find a set which is, roughly balanced. Right? At least, when the pseudo distribution is telling us that something is roughly balanced, we must find, a set which is highly non-trivial. We can't put most of the vertices on one side. And so that is really the problem in some sense, that is the main problem to attack in the context of normal, this ARB rounding for expansion. And, that's what we'll focus on for most of the second half. But before we go on to take a break, I want to tell you how we are going to accomplish this. Okay. And so the idea is kind of similar to this min-cut rounding that we were seeing before. Okay. So we already observed. So, let's like the idea is to, just look at this, look at the min-cut rounding a little bit closely. A little closely. So, if we map the vertices on the line in terms of distance from, some set A, then all of the vertices in A end up at 0. Okay. In particular, if I choose any threshold, any non-trivial threshold, so with probability 1, the set A would always be on one side of it. Right? Now imagine that I had a different set B. And, I could prove that B is, far from every vertex in A. Okay, so suppose I could prove that distance of J from A is larger than some capital delta for all J in B. Then I know that all the vertices of B sit at some point delta. Right? And so now, so I'm going to do the same kind of rounding, but now my hope is that if I pick a threshold, if delta is large enough, then it would generically happen that A is on one side of the cut, while B is on the other side of the cut. So now if I ensure that both A and B are large, then I will get a highly non-trivial cut. Okay, and so that's in fact the main idea. The main idea is to, characterize this in a definition. So let's call them, large separated sets. So A and B if, for all I in A, J in B, Dij is at least delta. In fact, let's call them delta separated. And they are large. And large means that, A times B is omega n square. Okay, so I'm going to call A and B large if, both of them are order n or omega n, and in particular, the product of their sizes is omega n square. And the distance of every pair of vertices, one from A and the other from B, is, at least capital delta. Okay. So now, I want to observe a very simple fact. So, very good. So here is like let's call it a proposition. If we round according to the line embedding dja, then expectation of xi minus xj squared, these are rounded values, some ij. Let's, now use the fact that we had two separated, well-separated sets to, now prove a lower bound on this quantity that we were not able to do that so far. Okay. So we know that, if I is in A and J is in B, then xi minus E of xi prime minus xj. So, okay, sorry. Let's Okay, so let's maybe write it down. So let's say that I'm only interested in the contribution from I in A and J in B here. That's certainly a lower bound. And now, what's the chance that I do the same rounding. I pick like a number T in 0, 1, and I take all the vertices that are small, that the distance from A is smaller than some T. Okay, so we are doing that rounding here. Now, what's the chance that an edge I comma j, where I is in A and B, j is in B, is cut? So this I and j are far away. That's what we're trying to use. We're saying that, okay, if you're far away, then you must almost always be cut. That's what we're trying to argue. Okay, it's like the reverse of this min cut inequality that we were arguing before. So what's the chance that, if I is in A and j is in B, that I actually cut? Well, it's going to be equal to, it's going to be at least delta, well, it's going to be at least d, good, it's going to be at least dja, yeah, it's going to be at least dja, because I put the vertices on line according to the distance from A. So the chance that I include J from B is at most D. Sorry, wait, right? Yes, okay, good. So the chance that I included a vertex J in B is at least dja, and in particular, this dja is at least capital delta. So this is at least delta times n square. Oh, it's delta times AB, which is omega delta n square. So let me just show why this is enough now. So remember, the two pieces that we've already argued. We've already argued that E of fgx prime is at most E twiddle fgx. And this inequality we just argued proves that, the denominator is at least the denominator under the pseudo expectation up to a factor capital delta. So, combining with 1 and 2, 1 and 2 imply rounding with approximation ratio 1 over theta delta. Good. So now let's take maybe questions for 30 seconds. If something was unclear, I'm going to do one more thing and we'll take a break. Questions so far? So I guess what I'm saying is, if I have two sets where every pair of vertices that go across those sets are delta separated, then now, I can actually guarantee that the denominator is at least, delta, a capital delta fraction of the denominator under E twiddle mu, and then I'm done. Because, I lose at most a delta factor in the denominator. I don't lose anything in the numerator, so I must be 1 over delta approximation. Questions? Okay, great. So
All right. I guess we just gotta wait, guys.
Okay, something bad happened. Peter, you're muted.
Your video's off. Oh, it's back now.
Yeah, what happened? Like, were you all on the call? Was it just me who got disconnected, or
It's just you. It looked like your Zoom just crashed or something. Yeah.
oops? Okay, all right. I thought nobody is teaching at 4 to 7 p.m., but apparently people are still learning somewhere around the world, I suppose. Okay, sorry about that disturbance. So, as I was saying, I'm going to state the existence and finding of these sets as a structure theorem that we'll focus on for the remaining part. So that G be D regular graph, let mu be a degree 4 pseudo distribution. And actually, the only consequence of being a degree 4 pseudo distribution that I'm going to use is the fact that, it satisfies the square triangle inequalities that we discussed earlier. So, we're going to define this dij's as before, 1/4 of which we discussed is a pseudo probability that I and j are separated in the pseudo distribution. So, the consequence, as I said, is that, D satisfies triangle inequalities. Good. So now here is an extra piece of hypothesis. Suppose that the average distance between pairs of vertices under this capital D is at least, some constant. Okay. I'll discuss this in a second, but I'm making this extra assumption. So let's call it extra hypothesis. Then there exists AB and can be found in polynomial time. In fact, we'll give an algorithm today such that AB is, omega n square, and wait. And for all I in A, j in B, dij is bigger than omega 1 over square root of log n. Okay. So this is, this delta quantity. So I'm claiming that, there exists 1 over square root log n separated large sets. And from what we just discussed, this gives you a square root log n approximate rounding, and so we are done. Once we have this theorem, we are done. Okay. And you'll see in a second that this 1 over root log n is what is basically the non-trivial part. We'll give a very simple proof right after we return, from the break, where, delta is 1 over log n. So, if we wanted to lose 1 over log n here instead of 1 over root log n, then it would be super simple. And, that would give us the proof of Leighton-Rao theorem from 88. It's not such a big surprise that, we can prove 12 plus 20 is like 32-year-old theorem quite easily. But, we'll do that. And then, we'll spend the rest of, about an hour on, giving a full proof of this structure theorem using global analysis. Good. So we'll take a 10-minute break. We'll reconvene at 5:45. Yes.
What in the extra hypothesis? It's greater than or equal to 0 to 1 or
0.1. Sorry. Yeah.
Oh,
So
okay.
good. So yeah, I guess I forgot justifying it. So this is saying that if on an average, if a random pair of vertices are well separated under the capital D distance, then I can find two sets which are delta separated and are large. Now, you can certainly imagine that if this hypothesis is like not true, then in fact it should not. Such a theorem should not hold. Imagine, for example, I get a pseudo distribution, which for whatever reason makes this average distance 0. If all pairs are like basically at distance 0 from each other, certainly I cannot find a pair of well separated sets because there are none. And so you can imagine that there would be some average pair is separated kind of hypothesis required That's what this hypothesis is. And of course, our pseudo distribution didn't come with this hypothesis. So I have to justify where this is coming from. In other words, like do something else when this is not true. And my do something else is always on a homework. So you'll prove like a little 4-line lemma which reduces the case where this hypothesis does not hold to the case where the hypothesis does hold. So eventually, this will be without loss of generality. The other way, okay. I hope I'll repeat this after the break, but one other way to saying this is that, like the pseudo distribution is saying, the pseudo distribution is giving you a, distribution over cuts. So this average distance being large, like because on a constant on average, basically saying that the pseudo distribution believes or, has its mass on omega n size sets, right? Because remember what dij's were. So, again, writing in yellow, this quantity is simply twiddle mu xi minus xj square. And this, we proved earlier that, if for an actual distribution, then this inside quantity looks like 1 of s times n minus size of 1 of x. And so, when this is, sorry, this should be 1 over n square, my bad. When this average is like a constant, this is saying that, the size of the cut on an average in expectation is, omega n square. The size of the cut is like on the one side, you have omega n vertices. Actually, both sides have omega n vertices. So this is saying that, without loss of generality, we can assume that, that the least expanding set is large. And actually, in some sense, this is also the worst case in some sense. Like if things are smaller, you can do other things. So it's not such a surprise that this is the hypothesis required here. In some sense, it's like the hardest case for rounding. So we'll do the hard case today, and then, we'll leave the easy case as a homework. Okay, so let's begin. So, one point that I did not say, but now I have like written in yellow in the notes is, the meaning of this extra hypothesis, which, we are not given. We don't know that actually holds for the pseudo distribution that we are working with. But the claim is that, in fact, that is without loss of generality, as in, if that does not hold, then we can somehow do some very simple operation and make sure that it holds. And, this one paragraph argument would be, one of the homework exercises you will do. But roughly speaking, what this hypothesis is saying is that, that a pseudo distribution is supported on sets which are, of theta n size. That's what basically it is saying, that, somehow the non-expanding sets that the pseudo distribution is pretending exist are in fact going to be, large. They're going to be theta n large. That's what this hypothesis means. And this actually in some sense is the hardest case. Good. So we'll prove the structure theorem now. We'll prove like there are these well-separated sets. So delta separated large sets. And in fact, we'll not just prove that they exist, we'll actually find it. Okay, good. So the proof would be, in a bunch of steps, but, remember, I told you at the beginning of the lecture that it's going to be global, okay? But before seeing this global proof, let's see a local proof that shows, a weaker version of the same structure theorem. And as I promised to you, this will allow us to recover the result that Layton and Rao, proved in '88, okay? So proof of weaker structure theorem. And, basically in this case, delta would be 1 over theta log n instead of theta square root log n. Okay. So let's understand how, and in some sense, again, the reason I'm doing it is not just because I can tell you about another new result, but another important result, but also because it's going to be kind of, motivate us what we are supposed to do right and wrong. Okay. Our final analysis will be motivated by improving on this basic analysis. Okay. So our goal, so remember, we don't even have to bother about the cut anymore. Our rounding is always going to be find a set A, put all the vertices on the line according to distance from the set A. And if A and B are large sets which are well separated, then, the numerator is going to be okay. And the denominator is what we are all worried about now. Okay, so that's all we are focusing on right now. So our goal is now simply to take a pseudo distribution, And as we we have this extra hypothesis that on an average, the pairwise distance between vertices is large. And our goal is to find delta separated large sets. Okay, so what are we going to do? Well, we're going to do something that we are very familiar with to begin with. We're going to take a Gaussian. So just like in the previous lecture, we can, because the quadratic hypothesis that appear, the quadratic polynomials that appear both in a numerator and denominator, are invariant under symmetrization. Like if I change x to minus x, nothing happens. I can assume without loss of generality that the mean of the distribution is 0. Okay, so this is what we've been doing essentially for all the problems so far for this homogeneous quadratic optimization. Each time, the polynomial is homogeneous, we can do that. So, so we're going to assume, so let's maybe remind ourselves that I'm going to assume that without loss of generality, the mean is 0. Let G be the Gaussian with mean 0 and covariance XX transposed. So, in particular, the expected values of any degree 2 polynomials in this Gaussian are going to be the same as the expected values under the pseudo distribution. That's basically what we guarantee because G has the same first and second moments as the pseudo distribution. Good. Now, in particular, what do we know? We know if I look at any particular coordinate, then expectation of GI squared is 1. That's because the diagonals of, e twiddle XX transposed are 1. And, EGI is 0. That's because, e twiddle mu of X was 0. Good. This is what we know. So now, we want to somehow construct delta separated sets. How would you start with? Well, one guess is that, look at this Gaussian. If Xi and Xj are separated in the pseudo distribution, remember this was Dij. So if Dij is large, then, we expect that the Gaussians that we get from the distribution should somehow, have far apart values. So Gi minus Gj should be, large. We'll do quantitative version in a second, but, the intuition is that because that's the expectation, that's also the expectation of the Gaussians that we just drew. So this is large. So in particular, we can somehow just, threshold on some value and take, one side of it to be, our guess for one of the sides A and, the other side of it as one of the sides B. Okay, that's what we're going to do. So we're going to let the preliminary guesses to be A0. I'm going to call it A0 because we're going to modify it in a second, but let's call them A0 right now. So this is a set of all coordinates where, GI takes the value at most -1. Okay, so remember, GI is mean 0 and has variance 1. So it has like I actually checked the chance that a Gaussian of mean 0 and variance 1 takes a value at most -1 is actually about 0.15. So, this set itself has to be of like 0.15 n size. So, sub omega n size. So that's not too bad, right? In expectation, it's like a theta n size set. That's very good. And I'm going to define B0 as the set of all J's so that Gj is at least 1. So it's like, I'm looking at things which are somewhat on the extremes. I'm ignoring the things in the middle because I don't know exactly how to argue about them. So I'm going to call these my initial guesses. Both of them in expectation have, omega and vertices. But actually, that's not enough. Because we don't just want that each of them in expectation have large number of vertices. Because, remember, what can happen is, it could be that A0 has omega n vertices in expectation and B0 has omega n vertices in expectation, but condition on A0 having omega n vertices B0 is basically empty. It could be true. We don't want that to happen. So, the first claim we'll make is that expectation of the product of their sizes is at least omega n square. And this is where, we are going to need this well-separated, like this extra hypothesis that the average pairwise distance was large. Okay, without that, this is not going to be true. So let's quickly see the proof because we've actually seen this kind of a proof for many, many times now. This is same as saying, what's the probability? So, I'm going to, again, usually, as usual, I'm going to analyze this locally so far. I'm going to understand what's the chance that some vertex I ends up in A0 and, J ends up in B0 for every pair ij, and then sum up. Okay, that's what I'm going to do. So the chance that gi is at most -1 and gj is at least 1. And now, this is the same kind of two-dimensional Gaussian calculation that we've done at least a few times now. So I'm not going to do it in detail. I'm just going to claim that this is going to be at least some constant times. And this time, because I don't bother about constants, we've lost way too many constants already, and we are going to shoot for like a root log n approximation. The constant does not matter. So, I'm just going to claim that there is some constant that relates it to the value under the pseudo distribution, which was like capital Dij. Okay. So basically the same kind of two-dimensional analysis that we did with vectors, etc., in the max cut rounding, we can do here and, get some constant. You can get this constant more explicitly too, but, we'll just claim that, this is what we get from there for some constant. Good. Very good. And, that's it, just like by linearity of expectation, you sum this up over all pairs I comma j, and you, derive that the expected product of the sizes is at least 0.1 times like the C here times n square. So C is, the loss I had in this local analysis of the rounding. And I know that the average of Dij's was, some 0.1. And so when I sum it up, I get 0.1 n square. So I'm getting 0.1 n square times some constant C. Okay, so that's good. This initial guesses for my sets A0 and B0, at least they give me large sets. We have not argued out or their separation at all so far, but at least they give me large sets, right? As I wanted. So that's good. And now, I have to understand. So now, what do we have to do? Like, now our goal is understand how Dij behaves for pairs I in A and J in B. Okay, so this is somewhat confusing. So let's make sure we understand. The choice of A0 and B0 is a random variable. It's a function of the Gaussian that we chose with the same first and second moments as the pseudo distribution. Okay, now the thing that we are really concerned about is this a well separated set? So it's large set in expectation, so that's great. We are now concerned about whether it's giving us delta separated sets, and this delta separation is defined with respect to the capital D metric, which by the way is same as the metric defined by expectations of the same Gaussian. So remember, Dij is same as E twiddle xi minus xj square, which equals expectation of gi minus gj squared. Okay, now notice, so we are trying to understand what's the chance that there is some pair I in A and j in B such that the expectation of gi minus gj squared was very tiny. Like we are trying to say that these sets are well separated. So we are interested in what's the chance that there exists I in A, j in B such that E gi gj squared is at most delta. Okay, then these sets are not delta separated, so that's the problem for us. So we're trying to understand what's the chance that it happens for some pair ij, right? Now notice that in the draw of the Gaussian that we're actually seeing, gj minus gi is at least 2, right? Because gj is at least 1 and gi is at most -1. That's how we define the sets. Okay, so this can be confusing, so I'm going to be redundant. It's all simple, but the notation can be confusing. So G's are actual draws of the Gaussian. Okay, we chose A0 and B0 to be defined by the coordinates where G sub i's are at most -1 and G sub j is at least 1. Okay, so clearly Gj minus Gi for any I and j which are in A and B respectively should be at least 2. So Gj minus Gi in the observed Gaussian is certainly large. Okay, we are worried that this is like some weird phenomenon, like somehow in expectation their distance was very small, but It just happened to be large in the random variable we happen to draw. That's what we are worried about. Okay. Now, if it were for a single pair I and j, this would be quite unlikely, right? Like if I make, like the Gaussians. So let's maybe do a back of the envelope calculation. So Gi and Gj are Gi and Gj are jointly Gaussian. And one fact that I think you proved in homework 0, if not, then I'm going to claim it, is that Gj minus Gi is also a Gaussian. It's like a scalar Gaussian. And we already know that its expectation of its square is at most delta, and its mean is 0 because individually Gi and Gj have 0 mean. So Gj minus Gi is a 0 mean delta, at most delta variance Gaussian, which is apparently taking a value which is larger than 2, and delta is small and 2 is large for us, right? So trying to understand what's the chance that this event happens. Okay, so by simple Gaussian concentration, the chance that Gj minus Gi takes a value 2 in this case is at most e to the minus 4 over delta. Okay, if this is unclear, then you can reduce it to the calculation for variance 1 Gaussian by just like dividing by delta here, like scale each Gaussian by like square root delta, and it's like a standard Gaussian then. And what we are saying is, what's the chance that the standard Gaussian takes a value which is like 2 over delta, or 2 over delta times the standard 2 over square root delta times its standard deviation. And so up to constants. Okay, it's weird. So this might, let me not claim it with like 4, but let's say O of 1, because I don't know the constants that appear in this inequality. But all I'm saying is, the chance that a Gaussian takes a value which is t standard deviations away from its mean is at most like e to the minus constant times t square. It's a sub-Gaussian distributed random variable. That's what should happen. So in general, if delta is, very tiny, like very tiny constant, then this would be like, an unlikely event. The probability of this event would be like a fixed but very small constant, right? That's great. But that's not enough, because we're not looking at one of these events. We're looking at many of these events. So remember, we are concerned that some pair I comma j, which was close, creeps into this. So a given pair creeps into our, potentially separated set with a very tiny probability. But we are interested in finding out if some pair creeps in. That's like a lot of pairs. That's like omega n square pairs that we're concerned about. So we can't quite deal with probabilities which are fixed. Like we have to do a union bound in some sense, or O of n square events. Each event, happens with e to the minus O of 1 over delta probability. If we have to somehow, control all these events simultaneously, then, the only bound we can guarantee, so, is so A0 and B0 are separated, are delta separated with probability, 1 with probability at least. So this is by union bound, 1 minus some n square times e to the O of 1 over delta. Okay, and now you see where I'm getting this log n from. If capital delta was like much smaller than 1 over log n, then this number, is much tinier than 1 over n square, actually any polynomial in n. So I can swallow this n square in the union bound, and I get like, with some 1 minus set of 1 probability, A0 and B0 in fact is a well-separated set. Okay, I'll take 10 seconds or 30 seconds and write this down. Until that time, you can ask me questions.
So are we conditioning on some event when we have the bound by e to the negative O1 over delta?
No, so the way to think about it is, think about all possible pairs where e gj minus gi square was at most delta. And delta is like some fixed value, right? So let's say it is like 1 over log n, right? Now
Sure.
we are trying to understand. So you constructed this, random variables A0 and B0, the sets where, GI were at most -1 and GJ was at least 1, right? So GJ minus GI in particular is at least 2. So you're now trying to understand what's the chance that a pair which was small, like its expectation of GJ minus GI square was small, what's the chance that it appeared to be large here? Because that's the only way it could have creeped on, like it could have somehow, appeared in this separated, like potentially separated sets, right? But we are saying, we are going to do a union bound over all possible delta small pairs. There are at most n square such pairs. For each pair, this bad event happens with probability at most e to the minus O of 1 over delta. And so, by union bound, this bad event happens. By union bound, none of these bad events happen with probability at least 1 minus n square times e to the minus O of 1 over delta, which means that if I choose delta much smaller than 1 over log n, then I would be able to avoid all these bad events. Does that help,
Okay,
Daisuke?
yeah. Yeah, I think I got it. Yeah.
Okay, great. So, we've proven latent row theorem. So, that's our second sledgehammer to crack a nut kind of thing that we did today. It's good, right? Like you at least got an order log n approximation right away. But now, and so I want you to notice that this was a local analysis. I mean, we did a union bound, which is like somewhat global, but really in some sense, we're analyzing each pair separately, right? So what we're going to do now is do a global analysis and improve on this and show, in fact, that delta equals 1 over root log n is going to work. Okay, good. So here is how we're going to proceed. So actually, let me set some notation for how we're going to proceed. So actually, let me say recovered latent Rao approximation for expansion. So that's great. Next, we're going to improve on this. Okay, great. So how are we going to do that? So, let's set some notation to describe what we're going to do. I'm going to define like a new graph H. This is not a graph which is input to us, okay? In fact, as you can see, we have completely stopped talking about the graph now. Like we did what we had to do with the graph already. We are like only concerned about its denominator. That term has nothing to do with the graph, okay? But I'm going to define a new graph, an auxiliary graph, if you will, just for the sake of notation, okay? Think of this, a good name for this is a short edge graph. Okay, this is basically the set of all pairs which are at most delta separated. So E of H is going to be the edge set of this graph is going to be, so it's going to be a directed graph. So I'm writing ordered pairs here. So actually, it doesn't matter if, okay, I guess both. So I'm treating it as a directed graph, but of course, both sides are present here. You'll see in a second why I want to call it directed. But basically, I'm collecting all pairs where the distance between them in the pseudo distribution I have is at most capital delta. Okay, so think of it as like the graph of all pairs which are, close by under the pseudo distribution where the distance is not so large. Okay, good. So now, what are we interested in? So in this notation, our goal is to find omega n size sets A and B such that if I look at A and B, then no edge of this graph H goes across it, right? Because E of H contains all the short edges. We would like that all the short edges be, on either, between only vertices in A or only vertices in B, but neither should be, edge of the form I in A and J in B. Okay. So our goal, so this actually, this kind of an object is kind of nice. It appears in combinatorics and it's called as a vertex separator. So, it's basically a subset or a pair of disjoint subsets of vertices which are large, and no edge of this graph H goes across these two sets. Okay, so it's a vertex separator in this graph H. So we're looking for a large vertex separator in this graph. So now I can now, give you a algorithm to find it, and then we'll analyze it. So remember, I told you I'm going to give you get algorithm to find these large sets. So my first step is going to be, the same that we did. But because my delta is going to be larger now, I can't actually argue that A0 and B0 themselves are delta separated. Okay, because I'm not going to do this union bound argument. I can't quite say that A0 and B0 are done. Okay, so now I'm going to modify A0 and B0. How am I going to modify them? So I'm going to find, so now there are some pairs which are close by but must have creeped in and go across A0 and B0. I'm just going to remove them. Okay, so find a maximal matching greedily in E of H intersect A0 cross B0. Now, here is where I'm using the fact that edges of H were directed. So, these edges are directed. They all are going to go from A0 into B0, not the other way around. Okay. You'll see in a second why I care about that. But what do I mean by greedy algorithm here? Just like, a priori and independent of the randomness of the Gaussians, set some fixed order on the edges. Okay, so let's say the order is 1, 2, 2, 1, 1, 3, 3, 1, 1, 4, 4, 1, and so on. And then, go to the next vertex and so on. Okay, just fix like one fixed traversal order on the edges. Okay, and then you do the following. Just traverse all the edges, take the first edge that is short, meaning it lies in E of H and is like goes across A0 and B0. Remove it, remove both the vertices that were incident on it and repeat. Okay, that's what I mean by greedy maximal matching algorithm. The important thing is that the greedy choices I made here, like the ordering for those greedy choices is independent of the randomness of the Gaussians. Okay, that's what I mean here. And then, output. So let's call this matching capital M. Let's call this set A0 minus V of M. B is B0 minus V of M. That's it. Like remove the vertices of the matching and you're done. Okay. So far I'm not doing something super non-trivial. All I'm saying is, I'm giving you like I'm giving you some precise method to remove, the pairs which were close by, but somehow, were ended up across A0 and B0. And, after I like remove those vertices from A0 and B0, I get like a resulting set A and B, and I'm going to output that. Okay, good. And of course, we care about how large A and B are. So we know that A0 and B0 were large, but then we, removed many edges. So now we are scared that A and B might be small. So of course, our goal is to prove that A and B are also large. Okay, in other words, that the matching, and we'll relate to the size of the matching in a second. Okay, so our goal is to analyze and prove that A and B are going to be large. Okay, good. So before we do that, I want to make like a few quick, simple observations, just so that, just to check that, all of us are not confused by any of the notations or all the various things going on in the proof so far. So one is that M is a random variable. Okay, remember that A0 and B0 are random variables because they were functions of the Gaussian I chose. Okay. And I then, found a maximal matching in the H set E of H. So E of H is not a random variable, remember, but A0 and B0 are. And then I found like, maximal matching in E of H intersected with A0 cross B0. So M is a random variable. Okay, good. 2 is what I've already told you before. M has directed edges. So why is this important? It's important because if Ij is in M, then I can conclude that Gj minus Gi is at least 2. Okay, and you'll see that, I'm going to use this fact very often. So I would want to remember the order of the edges in the matching M. Good. And the third thing I want to observe, and this will appear towards the end of the proof, it's actually very important. So let me call it a proposition, is that because the ordering that I processed the edges in this greedy algorithm for constructing the maximal matching was independent of the Gaussians, like independent of any other randomness in my algorithm, here is what is true. The matching obtained when G is the input Gaussian is reverse of the matching obtained when I give minus G as the input. Okay, so this is a very simple claim, but let me just like say 2 lines about it. If you took you took the Gaussian vector G, you drew the Gaussian vector G and you constructed A0 and B0. If you now imagine what would have happened if you got minus G, you basically get B0 for A0 and A0 for B0. Okay, so that's like the sides of the two things reverse. Okay, so now what this claim is saying is that because the ordering of the edges that we processed to construct this maximal matching was independent of the Gaussians, the matching I will construct when I'm given G as the input would just be, the same edges, except the ordering would be reversed. Okay, again, while I write the next stuff, feel free to ask questions. Okay, so I believe everything is clear. So one consequence of this fact that M of G is reverse of M of minus G, and sorry for this informal notation, but hopefully you understand, then the chance that vertex I appears with an incoming edge in M is same as the vertex, the chance that vertex I appears with an outgoing edge in M. This is because G and minus G have the same probability. The distribution is symmetric, the mean is 0. Okay? Feel free to ask questions.
Can you explain number 3 again?
Yes. So what this proposition is saying is that if I construct this maximal matching greedily, so remember it was a random variable, so it's a function of this Gaussian that I see, G, right? Now it's observing the following fact. If instead of G I had gotten minus G and I repeat the same algorithm, then the matching I would discover would be reverse of the matching that I discovered on G. By reverse, I just mean the same edges, like the same pairs, but the order of each pair is, reverse. So ij goes to j comma I. And, the reason this is true is because the A0 and B0 that you get on G and minus G are simply, flips of each other. So A0 goes to B0 and B0 goes to A0 if you flip G to minus G.
Okay, so I think, so in the greedy algorithm, the greedy maximal matching algorithm, you're like fixing like a permutation of the edges beforehand.
Yes, exactly. Okay. Yes. And exactly. It's important that the greedy algorithm does not correlate with any of the randomness. So it's a fixed order of edges that I'm processing.
Okay, got it. Thanks.
Good. Excellent. Very good. And yeah, so one consequence of that, combined with the fact that G and minus G have the same probability, or like the other way of saying that, the G hat means 0, so it's a symmetric distribution, is that, the probability that vertex I appears with an incoming edge in the matching is the same as the probability that vertex I has an outgoing edge in the matching. Okay, so good. Hopefully you all agree with these basic observations. So now, here is how we're going to use it. Well, I guess before we use it, I want to maybe make one simple proposition. If A, B, so you remember A and B is basically the vertex set, the subsets of vertices that we got after removing the vertices of the matching. Okay, so if A and B is small, so it's let's say little of n square, then the matching must be large. Okay, this is trivial, but let me just make sure that you understand this. Okay, remember how we did it? Like we had A0 comma B0, A0 and B0, like A0, the size of A0 times size of B0 was large. We proved it's omega n square. Then we took off the vertices, that appeared in the matching. So we're saying, well, the only way the resulting sets have small pairwise size is if the matching is large. Is this convincing enough? Again, feel free to ask questions. So I guess I'll call this the fourth easy observation. Very good. So now, okay, let's understand the idea of the proof. So what have we done? We are saying that, look, the only way we fail is if somehow, there is like this large matching, right? This omega n size large matching, of like short edges, of like delta short edges. Okay, that's the only way we fail. And you see, like, this is basically, each of these events was somewhat rare. We saw that already before, right? Each of the pairs that are appear for each ij in the matching, we know that E gj minus gi square is at most delta. We also know that gj minus gi is at least 2. So each of this is a somewhat rare event. And the way, like, collecting them into matching somehow, forces that these rare events are not happening because, okay, one way that many such rare events could occur is, if one of the GJs could get very large. Like, imagine that, G number 1 became like square root log n. It can happen. It's like a, if I have n Gaussians, there could be one of the Gaussians which takes value root log n. That can happen. And now what will happen is that all the vertices attached to it, about out of that, many of them will, basically be very large, right? Because GJ is very large. On the other hand, constant fraction of all the other GIs is like small. So GJ minus GI would be very large, right? What we are saying is, look, that's not the way this is happening. Because I took a matching, a single vertex only contributes one edge. So in some sense, we are saying, look, in some sense, these are giving us potentially, or like, somewhat less correlated set of rare events all occurring together. It's like, somehow I cannot attribute all of these rare events occurring to a single vertex being large or a few vertices being large. You're saying that a whole bunch of rare events have occurred. You want to say, well, that's not going to possible. That's not going to be possible. We're going to like somehow prove it's going to be impossible. Okay. So let's see how we're going to do that. So formally, what we'll prove is, let's maybe call this a lemma. So what we're going to prove is that if all of these rare events occur and the matching has omega n edges, okay, then we will prove that the maximum of the Gaussian variables is large. So, what we're going to do is like somehow observe that there were like many, pairwise vertex disjoint pairs, which were like, too large compared to their expectation. So what we'll do is like, we'll somehow chain them together and prove that, there is some I and j where gj minus gi takes a very large value because of the matching. Okay, so we'll prove that. So so this is basically the claim that the matching is large and the maximum must be large. So let me write it like this. Expected size of the matching. Don't worry too much about the quantitative part, like think maybe only about the qualitative part for now. So he's saying that, look, if the matching is large, like, like if this term E of, like if E of the size, expectation of the size of the matching is omega n, then this is a constant. Okay. And, this is about 1 over delta. So you're saying, look, if the matching happens to be omega n large, then the expected maximum of gj minus gi must actually be, 1 over delta large. Okay. On the other hand, we'll use some simple Gaussian concentration to prove that this actually cannot be more than order square root log n. This part should be less surprising to you. It's like gj minus gi's are Gaussians. Each of them have mean 0 and each of them have variance at most 1. So, the maximum of, n square Gaussians, you might imagine like a simple Hovding bound like a proof to show that, this is at most O of root log n. We'll sketch this too, but, this right-hand side should be less surprising to you. The left-hand side is what is the non-trivial part. We are saying that if there is a large matching, then we can somehow, get a certificate that the maximum gj minus gi, this pairwise distance between Gaussians, is large. And then, it's going to contradict the fact that maximum of Gaussians is not only O of root log n in expectation, but also is very tightly concentrated around it. In fact, so we'll use this very nice fact about, a maximum of Gaussians. So, we'll use, so let's actually write that fact right down right now. Let's see. Okay. So here is a fact that I'm not going to prove, but it's actually, if you haven't seen this before, it's kind of surprising. So let Z1, ZT be jointly Gaussian. Okay. Then the variance of Z1 up to ZT is at most O of 1 times the maximum possible variance of any of the ZIs. So what, in fact, in fact, the random variable max of Zi has a sub-Gaussian concentration around its mean. Good. So again, I'm going to pause for a bit and take questions. But what I'm saying here is that so it's not so hard to prove that the mean of a maximum of, let's say, variance 1 Gaussians, let's say T of them, is at most about square root log T up to constants. What this fact is saying is that not only is the mean about square root log T, the variance is actually quite small, somewhat much smaller than what you might expect. It's like, I have maximum of a bunch of random variables. It's a very complicated function. It's not some simple linear polynomial in ZIs or a quadratic polynomial, right? So in principle, you could imagine that its variance could be complicated and could depend on all of the variances or some of them or etc. Right? What this fact is saying is that the variance of the maximum of a bunch of Gaussians is actually at most the maximum possible variance of any constituent Gaussian. So in particular, if each of the Gaussians has variance 1, then the max random variable is concentrated with variance at most 1 or up to constants. It's kind of surprising, right? Like the max is actually very, very rigid. It's like in some sense, even though the mean is like square root log T, the variance is actually very small. It's like order 1. Okay, so this is actually, this is in fact like an instance of a more general fact. It actually holds not just for like a finite number of Gaussians. It actually holds for, what are called as Gaussian processes. And I don't want to define them or deal with them, but basically the same fact actually holds for Gaussian processes. The variance of the maximum of a Gaussian process, supremum of a Gaussian process, in fact is up to constants, basically the supremum of the variance of any of the constituent Gaussians. So in some sense, there is a way to generalize this observation to, infinitely many Gaussians, which have some geometric structure. So what that means is that, look, oh no, sorry about that. So what that means is that, if you look at this inequality above, you're saying, look, Gj minus Gi is a maximum of n square Gaussians. Its mean is square root log n is not that hard to prove using some Hovding bound. But in fact, it's going to be very, very concentrated, like with variance of variance of this max random variable will be about order 1. So, the chance that it takes a value much bigger than 2 root log n or 4 root log n is going to be like, very, very small. So I should almost never see it. On the other hand, if the matching is large, then in fact, I can witness some J and I where Gj minus Gi is very large. So the only way, this could be reconciled is that the matching must be small. And so that's basically, how we are done. Good. Very good.
Can I ask a question?
Yes.
This variance of Z1 to ZT, do you mean the variance of max?
Yeah.
Oh no.
You forgot the max. I was going to tell you.
Yes, absolutely.
Thanks. Otherwise, it doesn't type check.
Now it will. Good. Thank you for pointing that out. Any more questions?
Once you prove the matching size is small, then that implies that the number of edges is small between them. Like the number of edges in E of H.
Oh, I guess I didn't write it down formally, but if you remove the matching, then after the claim I'm making is so you start with A0 and B0. Once you take out all the edges in the matching, take out all the vertices that appear in the matching, then the resulting set must in fact be delta separated. Why is that? But imagine not. Then there must be an I in the resulting set and J is in the other side, which is a short edge. Then I could have added that edge to the matching and grown it, right? So it's clear that once I've removed all the vertices that appear in the matching, I'm done, right? And if the matching only had some small constant times n edges, then I could not have removed more than small constant times n vertices from either side.
Yeah.
So that's it. That's the argument. So does it make sense?
Yeah.
Okay, very good. All right. Okay, great. So let's see. It's looking like we may not complete the proof today, but that's fine. We'll do as much as we can and then finish it in the next time. Good. So okay, so we only have to prove this lemma is the point. Okay, we only have to somehow show that a matching can be used to construct a witness for the maximum of gj minus gi to be large. Okay, that's what our goal is from now on. Okay, so let's basically discuss the main idea behind it. The idea is to use the edges in the matching to do a certain chaining.
Pravesh, I don't think your screen is being shared.
Oh man, sorry about that. You're absolutely right. Now it should be shared. Okay, good. No harm, no foul so far, because I did not write anything except chaining. Good. So let's define hk of I as vertices within distance k in h from I. So now h was this set of short edges, remember, okay? So we're saying, okay, take the set of all vertices which can be reached via directed edges in E of h, starting with I. Okay, so this is the set of all vertices that can be reached. Okay, I should not call it distance because within k, within k steps. So this is not the weight, like this is not the sum of the weights, is I guess what I'm trying to point out. So think of the think of set of all vertices that can be reached in k steps in the graph E of h. Okay, and suggestively define the following quantity is the max of j in hk of I gj minus gi. Okay, so we're trying to understand how does gj minus gi behave for j's which can be reached in at most k steps, okay, from I in the short edge graph. And we're taking the maximum over all those j's. Okay. Now, intuitively, what we're trying to argue is that, remember, if I start with a edge in the matching, so if ij is in the matching, then it implies that gj minus gi is at least 2, right? Now imagine, but matching actually is always, matching is a subset of the short edges. So, this I comma j is also in, E of h, right? Now imagine that you somehow, you're at I, you took j step and you actually increase gj minus gi by 2. Now what you would like to do is, find another matching edge, if possible, to go, so, okay, so from j, clearly there is only one edge in the matching. So let's say you use any weird edge to go to some other vertex, let's say j prime. Okay, you go to a new vertex, and then somehow if j prime appears on the left hand side of the matching, then you can traverse another matching edge. Okay, so now you see what I'm trying to do. Like basically, I would want to construct a path where a constant fraction of them are going to use the matching edges in the right direction. Okay, and now my hope would be to prove that every one of these alternate edges which are not in the matching do not lose me anything, while each time I use the matching, I grow the maximum by 2. Okay, so if in expectation these edges only add 0 while these edges add +2, then if I build like a k length path, then I would actually get a witness that gj minus gi, like where j would be the last thingy here and I would be here, is at least like theta of the length of the path. Okay, so this is what I mean by chaining. I'm going to use the matching to chain together to form a long path where in expectation I would have used a constant fraction of the matching edges. The non-matching edges would not somehow hurt me, so that I would get a witness that the two endpoints in the path are going to be theta k away. Okay, so now if I build a long path, I would get like a witness for a maximum being too large. And then, I would get a contradiction as we discussed ago. So that's somehow the idea. So I'm going to use a large matching to show that I can construct, these long paths that form a witness for the maximum being large. That's the rough idea. Okay, good. So, in order to make this idea concrete, let's phrase this potential function. Let's define this potential function phi of k. So remember, yik is the maximum between maximum of gj minus gi, where j is reachable in the short edge graph from I with at most k steps. Okay. Now for every I can define this. For every I can define this maximum. So what I'm doing is I'm just summing up all these random variables, all this quantities yi sub k's, and calling that my potential function. So I cannot argue that a single I will grow, but I will prove that phi of k grows on an average. That's basically the idea. Like in some sense, this chaining idea is very easy if things were true, with probability 1 for every one of the pairs. Because they're not true, because they are somehow true, each of these things is true with a constant probability. I'm trying to do some argument that allows me to do this thing on average. Okay. So this potential function is a way to capture that. Notice with this definition that phi k over n is clearly a lower bound on the maximum, right? Like, because if phi k is large, then one of the yiks must be large, and that's clearly a lower bound on the maximum difference between gj and gi. Okay, very good. So now we have to argue. So so far we've defined phi k, and we have shown how it's useful for lower bounding the maximum. Now I have to somehow show that this potential function grows as k grows. So on an average, I'm saying that I can chain together matching edges to form like large differences. That's what I want to do. So that's what's going to be the next claim. Claim phi k plus 1 minus phi k is at least expected size of the matching. That's good. The matching being large should appear somewhere. Times order n, maximum I in n, j in hk plus 1 of I of expectation. Oops. So let me read out to you because I didn't plan my space very well here. But what this claim is saying is that, so far if you follow the proof, phi k is somehow trying to get at this, heart of this chaining business. And in particular, we have this lower bound that phi k over n lower bounds the maximum. We are now trying to show that phi k is large. Okay. So the way we are going to do is by proving that, as I grow k by 1, then phi k in fact must grow. So phi k plus 1 minus phi k should in fact go by something large. Okay. So how am I going to show it? I'm going to prove that phi k plus 1 minus phi k is going to be something which is proportional to the expected size of the matching minus some quantity, which, eventually I would have to control. But let's see what that quantity is. It's order n times the maximum of EGI minus GJ squared to the half. So it's like square root of expectation of GI minus GJ squared, square root of the variance of GI minus GJ. Okay. Where I is arbitrary and j is reachable from I in at most k plus 1 steps in the short edge graph. Okay. Now, don't focus too much on where these terms are going to come from because we are likely to do it only next time. Let me tell you why this is enough. Okay. So let's maybe go back and make sure that everything is clear so far. We are trying to do this chaining argument where we want to construct a witness to the maximum being large. So towards that, we define yik's, which is basically the maximum of gj minus gi when j is, reachable from I in at most k steps in E of h. Now, we observed that, so we have to somehow do this argument on average. So it's not enough to just look at individual yik's. So we define this potential phi of k, which is the sum of the expectations of yik's. And then, we observe that phi k over n clearly lower bounds the maximum. What we are now trying to show is that phi k is large. For that, we are making this inductive claim that, if I take one more step, okay, then I'm actually going to grow this phi k. Okay. And I'm going to grow by something that depends on the matching size. And, there is this negative term which I must control. And I'll show you how we can do it now. So let's in fact complete the proof using this claim so that we understand how it actually works. So remember that, so let's understand the second term here, okay? The term that appears on the right has maximum over I and j, which is reachable from I in k plus 1 steps of the standard deviation of the Gaussian gi minus gj. Okay. So now observe that egi minus gj squared, what's an upper bound I can give if j is reachable from I in at most k steps in E of h? Just to make sure that, the distractions and disturbances did not throw us off track. Can someone tell me what's the upper bound I can claim on this? So if j was reachable from I in one step, what would egi gj squared be upper bounded by? Remember, this is the same as dij. So if I and j were reachable in one step, then ij is an edge in E of h, in which case dij must be at most delta, because E of h was the graph of all short edges, right? So now if I and j are, at most k steps, if j is at most k steps away in E of h, then by triangle inequality, now this is the square triangle inequality, remember, this is not the triangle inequality for the Gaussians. We're using the fact that these Gaussians have the same second moments as, our pseudo distribution, and the pseudo distribution satisfies square triangle inequalities. So if, for example, I had j which is reachable in 2 steps, let's say ik and kj, then, dij would be at most dik plus dkj, which is at most 2 times delta. So in particular, because j is reachable from I in at most k steps in here on the right hand side, egi minus gj squared is at most k times delta. Feel free to ask questions because we're not completing this proof today. Okay, this is at most k delta, and now I want to describe to you why we are winning. Notice that we have, for whatever reason that I have not explained to you so far, I have a square root of this variance appearing here. So the second term here, so, RHS above is E of m minus O of n times square root k delta. Right, because we have the standard deviation appearing. We have variance to the power 1/2. Okay. So now we can see why we are going to win. So, so now, let k0 be, some number like this. So now, which is basically like, order 1 over delta. So this is the largest k0 I'm going to take. Okay. So then for all k at most k0, it's true that phi k plus 1 minus phi k. And now the reason I chose this k0 is because if you plug it in here, what do I get? I get, so, if I plug in any k which is smaller than k0 in k times delta, then I get, so let's do this calculation over here. K times delta is at most E m over n square times some small constant, right? So square root of this is E m over n times some other small constant, right? And it multiplies O of n. So altogether, the term that I'm subtracting out becomes, E of m times some small constant. Okay. And so now, you can imagine that if I play my cards right and make all constants work for me, then I should be able to make the second term, at most some half of expectation of the size of the matching. Which means that for all k up to this threshold value k0, I should be able to ensure that phi k plus 1 minus phi k is at least, let's say, some half of E of m. Okay? Okay, very good. So now what have we shown? Then in that case, I can show that max ij is at least gj, max of gj minus gi is, remember we proved is phi k over n. So I'll just apply it with phi k 0 over n. And, using this inductive formula, we get that, is at least half of, half E of m for every one of the k0 edges. That gives me k0 times E of m over n. Good. And now using the fact that k0 was E of m over n square over delta, this is theta 1 times E of m over n cubed. So that's basically, the lower bound I claimed on the maximum difference between gj minus gi earlier. Where did I claim that? Right here. So I guess what we just proved was that by this chaining trick, we can actually prove that we can find a certificate that the expected maximum of gj minus gi is at least, em over n cubed up to some constants. And we did this modulo this, potential increasing fact. Okay, so we haven't proven this fact today, phi k plus minus, how does phi k plus 1 minus phi k grow? But basically the idea is that we'll be able to chain together these edges of the matching to show that, for some large enough k0, phi k plus 1 minus phi k, as long as k is at most k0, grows as some constant times the size of the matching. And so if the size of the matching is order n, then in fact, we will derive a contradiction. Good. So, let me stop here as a formal end of today's class. And let me take questions because I think there were a lot of disturbances. I apologize for that, but hopefully we can clear it up right now. Are there any questions in the part so far?
Pravesh, you forgot a delta at the end, I'm pretty sure. Right.
Yes, in the definition, yeah, in the bound for k0, yes. So
Yeah.
k0 was E of m over n square over delta. So yes, I should get 1 over delta on the other side. So, the proof of this remaining part is not that hard. It's actually just, formalizing this chaining argument that we saw earlier. And so we'll do this in the next 10 minutes or so, at the beginning of the next class. But I think it's nice to make sure that what we did today so far is like roughly clear. So
Can
any
you
questions?
explain again the chaining part? Like how did you combine the two lemmas? The potential.
Wait, which part? The proof of the chaining part or the claim about how the chaining works? So we haven't proven this claim that is on the screen right now. We haven't proven, how phi k plus 1 minus phi k grows. Okay.
Yeah. Like you proved the final thing, right?
Yeah. Assuming this claim, what we proved was that, look, so we observed that, phi k over n is a lower bound in the maximum.
Yeah.
Right. So it's enough to prove that phi k is large. The question is, for what k's can I prove phi k large? I cannot prove it's large for every k because, I cannot like somehow construct these long paths infinitely. At some point I'll have to stop. Okay. So what this claim is helping me do is prove that, I can take the length of this path to be, something like E of m over n squared over 1 over delta. So the way to think about it is that if matching is a constant size, like constant times n sized, then k0 can be taken to be, square root log n.
Okay.
So remember, like capital delta at the end is going to be, 1 over square root log n. So what we are saying is that, we can somehow find about constant times root log n length paths that we can chain up to.
Oh, okay.
That's what this lemma is, that's what this claim is saying. And so we just like did that calculation to make sure that that's what the lemma indeed says.
Okay.
So we said, look, the term that is subtracted out here, is at most square root k delta times O of n. And, the second term is at most half of the first term, as long as k is smaller than this E of m over n squared over delta, which is like root log n when things are, what we want. And so we are saying, okay, up to about, root log n k's, this increase in phi k plus 1 minus phi k is at least some constant times E of m.
Oh, okay.
Okay, so if that is true, then, phi at k0 must be, the effect of chaining about root log n length thingies. Each of the matching edges gives me a factor 2. So it means that, I must have proven that the maximum is like some constant times root log n. So now if I play the constants right, it would be larger than the constant I can prove is an upper bound. That's the plan. So now, we'll implement this plan one step at a time. And the step we are going to implement now is like finish the proof from the last time, okay? So what I have here is basically, a summary of what we did the last time so that we can all page things back in and, get to the proof of the main chaining lemma. So recall what we were trying to do, right? We were trying to design algorithms for the problem of approximating expansion of a graph. And, we were considering only d-regular graphs the last time, right? So let G be a d-regular graph. We defined this quantity phi sub G, right? Which was basically the size of the normalized cut. Okay, the minimum size of a normalized cut in the graph. More specifically, if you take any subset of vertices, then, you can define this ratio, which is the number of edges going across the cut defined by set S. And the denominator is basically the expected number of edges across the same cut in a random graph, okay, which has the same average degree as, our regular graph D. Oh, one quick request, as usual, in all the lectures, if, you could turn your videos on, I would be grateful. It's again not required, but if you can, it would be great if you can turn your videos on. Okay, great. So yeah, so we defined this quantity, which we called as the expansion of the graph, right? We also, observed that this was the quantity that tells us, what's the chance that a random walk that begins at a uniformly random vertex in set S escapes S, right? And I said, okay, our goal is to approximate this quantity. We, started studying this fantastic algorithm of Aurora, Rao, and Vazirani. And, basically in the rounding form, this theorem stated that if mu is any degree 4 pseudo distribution, then there is basically a polynomial time algorithm that can find us a set whose expansion is at most about root log n times larger than whatever is the smallest expansion that the pseudo distribution is pretending. Okay, so on the right hand side, I have the quantity which basically, looks like the basically, so the right hand side, the quantity here is, is basically the value that the pseudo distribution thinks is the expansion of the minimum expanding set in the graph. Now, if it were an actual distribution, we should be able to simply find a S such that phi g S is at most, without any approximation factor, it should be the quantity on the right. But of course, it is not an actual distribution. So in general, we have to lose things. And what we're saying is that we don't have to lose too much. We have to lose only a root log n factor, okay, to do this. And we basically, began the proof of this. And if you recall, oh, and I should point out that the only way we were using degree 4 part of the pseudo distribution was that this pseudo distribution satisfies the square triangle inequality that you proved on your homework. Okay, good. So very good. So then, what was our rounding like? We said, we started by observing a very simple algorithm for min cut and also the step 1 of our rounding. We said that, if you take any subset of vertices, if you take any subset of vertices, let's say A, then, we can do the so-called random threshold rounding. Okay, what did we do here? We said, let's compute, for every vertex I, the distance of I from A. And the reason we could call, so remember this quantity D that we defined, dij was simply 1/4 tilde E mu xi minus xj squared. Okay. And the reason we can call it D, or D for distance, is because, you know, it is a legit distance because of square triangle inequality. So this is, you know, this would not have been a distance if we didn't work with a degree 4 pseudo distribution. But because we have a degree 4 pseudo distribution and it satisfies the square triangle inequality, this D is indeed a distance. And with this D, we can define, you know, this 1D embedding of all the vertices into points on the real line. In particular, the ith vertex goes to the distance of I from, you know, the closest vertex in set A. So for any set A, I can define this 1D embedding. And then we said, you know, just pick a random threshold in 0, 1 and take all vertices where DIA is, you know, smaller than this threshold T. We said, okay, if you select this cut, then in expectation, the size of this cut is at most, so this is the expected size of the rounded cut. We said that here, you know what, if you do this, then the expected size, that's point number 2. The cut size in expectation is at most the cut size, you know, of the pseudo distribution. So in particular, you know, we sketched how we can use this to obtain a, you know, polynomial time algorithm, yet another polynomial time algorithm for calculating the min cut in a graph. That was nice. And we said, okay, you know, will now almost be done if we could prove that, you know, the denominator of this rounded guy is, you know, not too much smaller than the denominator of the pseudo distribution. So which is like basically the inequality in the opposite sign, right? Like in the numerator, we would want a rounding which gives something which is at most that of the pseudo distribution's value. On the denominator, on the other hand, we would like something that gives, you know, not too much smaller than the denominator in the pseudo distribution. And we said, okay, our goal in fact would be to prove that there is a way to find this set A. So there is a way to calculate this set A. So, you know, the first 2 bullet points here hold for arbitrary sets A. The third point, what we are going to prove, what we started proving, is that there is a correct choice of A that we can make, such that for that choice of A, the denominator is, you know, at most a root log n factor smaller than the denominator under the pseudo distribution. Okay, this was the main part. And we observed that this part has nothing to do with the input graph. This is entirely, you know, a statement about a pseudo distribution, you know, without anything to do with the input graph at hand. And we observed this cool fact that, you know, one way to establish that, you know, this point number 3 holds here was to basically find a pair of well-separated sets which are large, right? We said if we can find a subset of vertices, let's say A and B, such that both of them have omega n size, and if I take any vertex in A, any vertex in B, then the distance between them is bigger than some capital delta, where delta is going to be like this 1 over root log n eventually. Then we call such a pair of sets delta separated. And we observe that, you know, if we find omega n large delta separated sets, then in fact, we can prove this bullet point number 3 here with this, you know, a factor replaced by a capital delta. Right? So far, so good. And, you know, this was the main structure theorem that Arora, Rao, and Vazirani proved. We started proving this. So let me, you know, quickly walk you through how we were doing this. And then, you know, and we'll basically prove the remaining lemma in this proof. But this was the main part of the proof, right? This was the main structure theorem. And we said, you know, the key part here is that this 1 over root log n, in some sense, is the result of a careful global analysis of the Gaussian sampling that we've been doing for a while now, right? We said, in fact, we observed that if you just do a simple local analysis, then in fact, you know, you can prove the same result with capital delta equals 1 over log n instead of 1 over root log n. And we observed that that's one, you know, simple way to recover this result of Layton and Rao from 1988, which gave a log n approximation for expansion. But of course, we said, you know, we are going to work a little bit harder to get this root log n approximation, and that would involve using global analysis. So how did the analysis go? Well, we formulated this auxiliary graph, you know, on the same vertex set, where the edge set basically meant that, the edges basically were all the pairs which were, closer, at most delta away according to its distance d, right? We formulated this graph of all close by pairs or short edges, right? We started with like initial rounding. We calculated sets A0 and B0. So we took a Gaussian with the same first and second moments as a pseudo distribution. We said, just take all sets of all vertices, such that the Gaussian has coordinates smaller than -1 on one side. Let's call it A0. Similarly define B0. Now we would be done if A0 and B0 were separated. We proved in fact that A0 and B0 are omega and large in expectation, but the key point was, are they separated? That means that, is there a I in A0 and J in B0 such that Ij, which are at most delta away? If such a thing exists, then A0 and B0 are not separated. And in general, we were not able to argue. In fact, it's not true that A0 and B0 are going to be separated. So we, devised this scheme to improve A0, B0. We said, we'll basically find a maximal matching in, the intersection of this graph EH of close by edges and, the edges that go from A0 to B0. So if A0, B0 is not separated, then there must be an edge that goes from A0 to B0, which is, a small distance away. So we, removed a maximal matching in this graph. And we observed that once you remove the maximal matching, the resulting set is trivially delta separated. Good. The resulting set is trivially delta separated. But of course, the main question is, have we removed too much? In particular, is the remaining pair of sets A and B still large? This was the main question that we were, trying to answer. And, our idea was that if in fact there was a large maximal matching, which is the reason for why we would have removed too many vertices, then we wanted to somehow, show that we can chain together the edges of the matching to produce like a rare event that should never have happened, right? And our rare event was basically, how large is the maximum of Gj minus Gi over all pairs I and J. So this Gaussian was, the Gaussian vector was chosen at random with the same first and second moments as the pseudo distribution. And, what we were trying to do was that use this matching, use the fact that there is in fact a large matching to construct a lower bound on the supremum of Gj minus Gi. And then, we wanted to just combine this with the observation that this is the supremum of a Gaussian process, which just means, take a jointly Gaussian random variables and take the maximum of the projection of it in any bunch of directions. So this is, a bunch of linear functions in Gaussian, and you're taking the maximum of them. So it's a Gaussian process. We, what we observed was that, this is a Gaussian process. So it has, in fact, a very strong concentration around its mean. And so, we would be able to derive a contradiction if the matching is too large, because the matching being too large means that the supremum is large, but the supremum is going to be small with very high probability. And so we can like chain these two conclusions together to derive an upper bound on the size of the matching. Okay, this was basically the structure of the proof. Okay, hopefully you all have paged this back in. And the key remaining lemma, so we argued essentially everything except the main chaining lemma. So let me remind you what the chaining lemma was. So again, Dij is this distance that we defined using the pseudo distribution. Then, we formulated the chaining lemma in the following way. So we said fix any vertex and let Hki be the set of all vertices which are reachable by following at most k short edges. Okay, so at most k edges in the graph H of short edges. Okay, so this is Hki is a set of all vertices that are reachable from I in at most k steps. And remember, E of H was a directed graph. We stressed this the last time. And then we said, let's define these sequence of random variables Yik, which calculates the maximum of Gj minus Gi, where J is reachable from I in at most k steps. Okay, that's what we said. And of course, if I let k tend to infinity, then this becomes the maximum of Gj minus Gi. So for large enough k, basically, if I show a lower bound on Yik, I would be done. But in some sense, we said the whole point of the proof was to do this argument in average. Like we can't quite argue that this would work for I itself. Instead, we would argue in average that it works for some pair I and j. And the way we did that, the way we planned to do that was by formulating this potential function, which calculates the average of this random variable yik as you pick I at random. Okay, so this is formulated as a sum, but we are trying to somehow show that the cumulative is large. And then we observe that if phi k is large, then basically it means that one of them is large. So clearly we get a lower bound on the maximum of gj minus gi in terms of phi k over n. Okay, so this was the easy part. The main chaining lemma was designed to prove that phi k must be large. And the way we did that was by proving that, phi k plus 1 and phi k must be, somewhat different. So phi k plus 1 must be somewhat larger than phi k if the matching is large. And so the key statement that we wanted to prove was that phi k plus 1 minus phi k is at least the expected size of the matching. So in particular, if this is large, then we are going to win, minus some term, which hopefully will be small. So what's this term? It's O of n times the maximum of EGI minus GJ squared, okay, which by the way is same as DIJ, right? Because the Gaussian G has the same second moment, first and second moment as the pseudo distribution. So this inside guy is just Dij. So the maximum is over Dij to the 1/2. Okay, over all pairs I and j, so that j is at most k plus 1 distance away from I in the short edge graph H. Okay, so we said, if we prove this, then we are in fact done. We in fact scheduled argument. The rough argument, if you remember, was basically that, we can upper bound what gi minus gj squared is, because, j is at most k short edges, k plus 1 short edges away from I. So we observed that, this expression would be at most, so the inside expression would be at most k plus 1 times delta, because each edge is delta short in the graph H. And so, we basically, this term roughly contributes up to constant factors square root of k plus 1 times delta, right? And then, we observed that, if we correctly, so this is also order n, this is also order n. And so, we observed that, we can somehow pick k, which is about root log n, and make this argument work out. As in, like, this phi k plus 1 minus phi k1, if phi k plus 1 minus phi k is large, like is omega n, as long as, k that we pick is at most, some 1 over, so k is at most like order root log n. Okay, so this was the part we did the last time. The part we assumed is what we're going to prove today. We're going to prove that, this increase in phi k plus 1 minus phi k indeed is true. We're going to prove this lemma today. Okay, so sorry, that was like a quick summary of what we did the last time. So let me, just take a 30-second pause and see if there are any questions about the plan from the last time. And then we'll go ahead and prove this.
Sorry, could you just say again, why does k root log n suffice if you assume this?
Right, okay, so that's the power of using the same scribble. We can go back up. So let's see, where did we prove that? Okay, there it is. Okay, so here's the calculation that we did the last time. I suppose the screen is not frozen and this is visible to you, right? Okay, so we observed that, if we take any k which is smaller than this e, so this is just some small constant. So we're going to think of the setting where e of m is omega n. So this is just a constant. So clearly, what this, so we are basically saying, imagine that we pick k0 to be at most some small constant over capital delta. Okay, then this term would contribute, some small enough constant, the second term, right? So if the second term contributes a small enough constant, then, we get em minus some small enough constant times on. So if this is bigger than some constant times n, and this is smaller than some small enough constant times n, then we get basically a omega n lower bound on the right hand side. Still good?
Yep.
So the point was that all that remains to prove now is all that remains to prove now is where is that? This increased lemma. I mean this inductive increasing lemma. Any more questions so far? Okay, very good. So let's go ahead and prove this, and then we can come back and take a look. If we understand the whole proof. So here is basically the first observation, which is clearly easy to make, which is that if I look at, so remember yik was the maximum difference between gj and gi, where j is reachable in at most k steps. So now, if I look at yik plus 1, then I claim that yik plus 1 is at least yj plus gj minus gi. Okay, what is this statement saying? So the way is basically observing the following fact. Let me maybe draw here. So let's say that you chain together and you have some vertex, let's say v here, such that gv minus gj is large. Okay, so and v is reachable from j in at most k steps. Then I can just add one more step. If v is reachable from j in at most k steps, and j is reachable from I in at most one step, so if ij is an edge, in other words, then v is reachable from I in at most k plus 1 steps. Okay, and so clearly any lower bound on yjk gives me some lower bound on yik plus 1 by just adding gj minus gi for this one extra edge that I'll traverse. Okay, so this tells us that yik plus 1 is always larger than yjk plus gj minus gi for all ij that form an edge in the h graph. Okay, and so this pictorial proof is basically equivalent to claiming that hk plus 1 of I is contains the set of all vertices which are reachable in at most k plus 1 edges in this graph from I contains the set of all vertices that are reachable in at most k steps from j. Okay, true because. Okay, very good. And so now you see what our idea is, right? If ij is also a matching edge, then we observe that gj minus gi is at least 2 for every edge ij in the matching. In that case, yik plus 1 would increase by plus 2 on yjk, right? And so our plan now is somehow to find a way to chain using this matching edges, so that we can construct a lower bound in the maximum of gj minus gi by capturing as many matching edges matching edges ij as possible. Okay, that's our plan, and the matching is huge, so that's supposed to help us here. Okay, so the way we will phrase this argument, we will actually now, or not all edges are in the matching and not all vertices are in the matching, so we'll create like a dummy matching. So let n be be an arbitrary matching. I don't care what it is, but it's a matching of vertices that are not in this matching M. Okay, so let n be an arbitrary matching. So then, as we said, observe that, you know, for all ij in the matching M, gj minus gi is at least 2. So in particular, for all ij in M, yik plus 1 is at least yjk plus 2. And here's like the fact about the dummy matching, which is easy, but it's going to really help us. So let's write something for every edge in this matching N. So I claim that half of yik plus 1 plus half of yjk plus 1 is at least half of yik plus half of yjk. So now, till the time I erase this stuff, can someone tell me why this line is true? Feel free to unmute yourself. Why is this line true? It's like it's almost like a trick question. It's supposed to be immediate, but just so that I know everyone's following, can somebody unmute themselves and tell me why this is true?
Because y to the k is increasing with k.
Yeah, exactly, right? Like all the vertices that are reachable in at most k steps from I are also reachable in at most k plus 1 step from I. So yik plus 1 is always larger than or equal to yik. And yjk plus 1 is at least yjk. Remember, yik is the maximum of gj minus gi for all j which are reachable in at most k steps from I. Okay, so I hope this is you know, absolutely clear to everyone. Feel free to ask questions otherwise. Okay, so that's good. So now, you know, let's see what this means. Okay, so here is a, so this is an inequality for, you know, for all matching edges, matching M edges, and this is an inequality that holds for, you know, edges in matching N, and M union N is a matching of all the vertices, right? So now, if I sum up all these inequalities, what do I get? I get I equals 1. So let me write it down. So maybe it says summing up. Sum from I equals 1 through n, yik plus 1, li, so let me describe what li and ri are. One, if I has an outgoing edge in M. 0 if I has an incoming edge in M. And half if, you know, I is unmatched in M. And Ri is basically the analog of it. So let me write it here. Ri is 1 if, so incoming in M, 0 if outgoing in M, and half if unmatched in M. So, you know, this is simply a notational trick that I'm doing right now. But, you know, my goal is, you know, I want to have like a sum over all vertices I on the left and all vertices, you know, on the right. So what I did was, you know, if I sum up all these inequalities, what do I get? You know, from the first part, I get all the left vertices in the matching M, right? So from the matching M, I collect all the vertices, the I, for which, I collect yik plus 1 for all vertices I, which are on the left side of some edge in M, right? So that gives me yik plus 1, right? And I get 1. So Li is 1 if, I has an outgoing edge, which means it's on the left, and 0 if it's, has an incoming edge. Now, if I doesn't have, if I doesn't have, if I is not matched in M, then I'm simply giving it the value half. Okay. Why is that? Well, because, if I is unmatched in M, then it appears in N, and there, all coefficients are half. Okay. So same argument applies to the Yj. If J is matched in M, then either it's matched as a left vertex or a right vertex. That's basically what this Rj is doing. And when it is not matched in M, Rj just collects a half, right? And because I summed up M number of inequalities from the matching side, I get 2 times M on the right hand side. So again, is this part absolutely clear? Good. Simple, not that hard so far. Now here's the nice part. So if you remember, when we constructed the matching, we said, we are going to construct this matching M greedily by, just traversing through edges in some predefined order that does not depend on the randomness of G. And as a consequence, we derived that, the chance that a vertex, so, we observed, in fact, this fact, we observed that the matching that we produced on Gaussian vector G is basically reverse of the matching that we produce on minus G. And because G was a symmetric distribution, we observed that the chance that I appears as an incoming, the chance that I has an incoming edge in M is same as, it has an outgoing edge in M. So remember we observed this fact the last time? We're going to use that now. That fact implies that for every I, ELI equals ERJ is half for all I and J in N. So again, can someone unmute themselves and tell me why this is true? I mean, I kind of described the reason, but I need confirmation.
Yeah, the probability of being 1 and 0 is the same.
Exactly. And that's all we need is a point, right? Like I can be unmatched some number of times, but whenever I is unmatched, Li is just, fixed to be half, right? So the only thing we need to prove this is that, Li takes the value 1 and 0 with equal probability. And that's just true because of, this fact that Mg is the reverse of M of minus G. Again, absolutely clear? So, okay, so this looks good, okay? So why does it look good? So here is, what I would like to do. Here's a, like, think of it like a thought experiment. So, we had this inequality at the top here. So which said sum I, yik plus 1 li is bigger than sum I, yjk rj plus 2 times m. We are trying to somehow, remember, we are trying to argue that. So if you remember, we have phi k plus 1 is expectation of yik plus 1, the sum, right? So this right hand side kind of looks like phi k plus 1 if I take expectations. In fact, let's take expectations. What's the big deal? If I take expectations, by linearity of expectation, I get this inequality. Now, the left hand side almost looks like phi k plus 1. This term almost looks like phi k. And, I have something that's increasing, something that basically depends on the matching size. So this kind of seems like we're there, right? It says that phi k plus 1 minus phi k is growing with the expected size of the matching M, right? Except we are not quite there yet because of this LIs, right? We don't quite have yik plus 1 and yjk here because they come multiplied with these LIs. LIs, remember, are random variables. and they could be correlated with yik plus 1s. So in general, we have no guarantees that Li's and yik plus 1 are independent. Right? They are like jointly distributed as the Gaussian random variable. So in general, there is correlation. But our hope is somehow to replace this by half of, so somehow, our hope is to somehow pretend as if Li's and yik plus 1 were independent. If they were independent, then, the expectation of yik plus 1 times Li would be, expectation of Li times expectation yik plus 1. We just argued that expectation Li is half. So that will give us half pk plus 1. Right? So if we could somehow pretend that they are, almost independent or independent, we'll be done. And so that's the idea. We're going to simply do an argument which kind of allows us to replace expectation of the product yik plus 1 times Li by the product of their expectations. And then we'll basically, account for whatever is the difference in the error. So the term that you see on the right-hand side, this O of n times blah, 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 that's simply going to come from the error here. Okay, so let's do this. So here is, so, let me maybe write it in a way that's readable later on. Okay, good. So that's where we are now. So what we'll do is, just try to understand, what happens, what's the difference between, the expectation of the product and product of the expectations. So here is a claim. Actually, this quantity, if you've seen before, this is just the covariance of these two random variables. So remember, I can write covariances like this. Good. Still following? And now, I'll use the one grade inequality that actually we are going to use many, many times, in this class. It seems like it's the first time we're using it right now, which is kind of surprising. We're going to do Cauchy-Schwarz inequality on this. Still with me? That's the difference of, these two random variables. That's certainly an upper bound, on the difference in product of expectation and expectation of the product, right? Now let's look at what these two quantities are. This is the variance of the random variable Li, correct? And this is the variance of the random variable yik plus 1, which is not so surprising. All we wrote down here is that the difference between the expectation of a product of random variables and the product of expectations is at most, the square root of the product of their variance, which is, not a surprising fact. It's a very basic fact in statistics. So now let's understand, how large can these quantities be? So Li is a random variable which takes values in, 0, 1. So in fact, it takes a value 0, 1 and half. So, variance of Li is at most 1. That's all I'm going to use. Okay. Agree? So let's, worry about variance of, yik plus 1. So here is a fact that we wrote down the last time. We said, this is a cool fact about concentration of maxima of Gaussian processes. Said, variance of a bunch of jointly Gaussian random variables is at most O of 1 times the max variance. So variance of max is basically, you know, up to constant factors, at most the max variance of any of the constituent random variables. Okay. So now, why is this relevant for us? Well, because yi plus, remember yik plus 1 is basically the max over, you know, j in hk plus 1 I of gj minus gi. So it's max of a bunch of Gaussian, you know, correlated Gaussian random variables. So the variance of yik plus 1 is at most max variance j in hk plus 1 I of gj minus gi. So gj, gi, remember, were mean zero random variables. So gj minus gi is a mean zero random variable. So this is, you know, expectation gi gj squared. Sorry, it's variance. So let me, yeah, that's what the bound of the variance is. Agree? Again, feel free to stop me if things are confusing, but you know, this is basically a simple proof now. So you know, we have we basically just literally computed the variance, or an upper bound on the variance, right? And there is a O of 1 thing. This O of 1 is basically this O of 1. So that's great. So now, you know, we are basically done because we have a square root variance of yik plus 1 appearing on this side times something, a quantity which is at most 1. So, you know, we have derived. So, you know, so we basically can conclude that EYIK plus 1 Li minus the product of their expectations is at most square root variance. So is at most square root EGI minus GJ squared for, you know, J in, okay, sorry about that. Max in JHK plus 1 I EGJ minus GI squared. Very good. Up to, you know, constant factors. So this is O of 1 times this. Okay. So far so good. So we know we do the same argument on the right hand side. So remember, we have these two expressions. So we are going to replace this expression by the product of the expectations of the random variables inside. We're going to do the same thing with this guy. The same variance bound that we just computed, the same bound that we computed on the difference in expectation of the product and the product of expectation applies on the right hand side. We replace each of these quantities by the product of their expectations inside, right? And we account for all the difference that we incur as an error. Okay. And so we already observed that if I replace these two quantities by their expectations, I basically get half of phi k plus 1 on the left, half of phi k on the right. So now you see we are done, right? So a similar argument gives E y j k r j minus E y j k E r j is at most O of 1, you know, max of j in h k I gj minus gi squared. Same kind of exact argument. And now, you know, we just account for these errors and, you know, basically say that, well, we are okay to incur that loss additively. And so, you know, instead of writing it out in full, I'm just going to say that, so plugging in these bounds finishes the proof. That's it. Okay, so what have we established? We basically proved that phi k plus 1 minus phi k. In fact, you know, we kind of proved a precise constant factor. So we had, you know, I think 2 times expectation of m appearing. And actually, these two appear with half. So we get, in fact, 4 times. I mean, I'm not trying to pretend that I'm saving constants here, but just trying to prove that, you know, at least this constant was clear. So we've done. We are basically done with this chaining lemma. We've proven, this average version of the fact that we can use matching edges to construct the lower bound, on the maximum. Okay. So let's take, maybe a minute of questions, and then, we can shift gears and start our new scribble.
Pravesh, you need to take the max over I also at the end.
Yes. I also need to take max over I. That's absolutely correct.
We didn't have to match all those vertices which were unmatched in M, right? We are just adding the inequality.
Yeah, I mean, this is, introducing this capital N was a notationally pleasing way to do the proof.
Okay.
There's, of course, as you're absolutely right, we could simply have done this proof with the constant factor of the vertices that appear in M. But then, you to introduce some more crazy notation.
No, I was saying we are just adding half yk plus 1I is greater than half yk I for all the vertices I which were not matched.
You're saying that
Before
you're
the
not trying to gain anything from the other matching, right?
Yeah.
Yes, absolutely. Yes.
Yeah, and that also assumes N is even if we want to have another matching.
Ah, right. That's an excellent point. We are assuming N is even, and that's kind of without loss of generality. I mean, I could simply say that solve the problem on even vertex graphs, but you could also just add a dummy vertex.
Yeah.
You can always make N even without loss of generality. It's a good point that I
I'm
use
just
N is
saying,
even.
we need not do the matching at all. Yeah.
Say it again.
I was just saying we need not use the matching at all. I mean, the other matching.
Yes. Yeah. So, like the capital N matching I introduced exclusively for nice notation.
Yeah.
So I had a question from last time, which maybe I will not get totally right, but I guess there's all of this work in getting multiplicative approximations, like log n and then root log n.
Okay.
But if like we wanted to get an additive approximation, like we know that the problem is easy when the size of the sparses cut is like really small. Or sorry, it's hard when the sparses cut is really small, but if you're only looking for like an additive approximation, then like this isn't such an issue. Do people think about this at all? Or
it's a, let's understand. So I think I want to say that some additive approximation follows simply from Cheeger's inequality. So as you observed, the additive approximation is meaningful only when the expansion is larger than a constant, right? Otherwise, it's trivially going to be true. Otherwise, it's like additive approximation is like trivially going to hold. And then once phi g is the true phi g is at least a constant, we saw that there is a way to get root phi g. There is a way to round a degree 2 pseudo distribution to find a cut whose expansion is at most square root of phi g, which is again a constant approximation. So you can make it an additive guarantee. Does it make sense?